It's better now. Do you hear me? Thanks for letting me know that I was muted. Okay, perfect. Yeah. So, hi everyone. Thanks for being here. I was just saying that it's been a while since I've done one of these, so I'm a bit rusty. Please bear with me. For those of you who don't know me, my name is Ajay. I write software, mostly high performance software. My background is in compilers. I have a PhD in compilers actually. I just recently finished my PhD back in August 2025. And it was a 7 year long PhD focused on building DSL compilers, high performance compilers, high performance libraries, all the fun stuff. And I used to do these streams before where I used to write some uh, high performance implementation. We also wrote some sort of an emulator for an NES game system a while ago, but I eventually got busy. I was close to graduation. My thesis needed some work. I was going around giving talks. That was taking a lot of my time, so I decided to put that on hold for a bit. And then now that I'm done, now that sort of my life has settled a little bit into a regular routine, I'll tell you about what I'm doing right now in a bit. But uh, I thought it might be a good time to bring this back. And then obviously a few weeks ago, or actually not a few weeks ago, last week they announced the Anthropic C compiler, and that created a huge ruckus in the whole online software development community. And I thought this is a good opportunity to talk about compilers again. I'm not gonna say too many opinions about what I feel about that compiler. I think there's definite positives to it. There's definite shortcomings to the compiler, but I think it creates like it brings up an important question. Like, do all compilers have to be optimized for performance? Do all compilers have to perform type checking? Do all compiler implementations have to be readable? Uh, I think the answer for the third one is pretty clear. I think they need to be readable, they need to be modifiable. That goes generally true for all uh, pieces of software. But the first two questions, I think the answer is yes or no, and I will try to answer that up through this stream. Is there any use for compilers that are not optimizing? Is there any use for compilers that do some bare minimum type checking, don't implement all the language features, and can they still be useful? But before we get there, let me tell you about what I have been up to since last year. So, like I said, I defended my PhD in June. I submitted my thesis in August, and since then I've officially been done. And then I immediately started this company called Build for Sim. It is going well. It's been what, 5 months now since we started it. It's a company that's focused on optimizing spice simulation, so circuit level, transistor and level device level simulations. And the whole big picture idea is we're using my research. It's a good application for the stuff that I've been working on for the past 7 years. And yeah, and that's what we're doing. We are looking at optimizing ngSpice, bsim4 models, and stuff like that, and using compiler techniques for that. Maybe I'll get into some details about it later as we go through the stream. But yeah, so let's get to why I want to do this stream. If you're here, you know the title of this stream is centered around writing a C compiler in x86 assembly. I have actually put together a small website here under my website where what we'll do is as we go through this development, I'll keep adding stuff to this website so that there's sort of like a log of all we have done. Most importantly, what this will have is all the language constraints we'll add. As you can imagine, 8 hours is absolutely not enough to write a full-fledged feature-complete C compiler. But what we'll be doing is we'll be restricting the language in interesting ways to simplify the implementation, to reduce the work, but still keep it useful. And what I'll be doing here is I'll be listing all those constraints, those design choices we're making, so that later on we know what really is this compiler. So why did I want to do this? Like I was saying, I wanted to answer the question, is there a use for compilers that are that are not perfect. And one of the answers for this, I think there are many answers, but one of the answers I think is bootstrapping, right? And what I mean by bootstrapping is writing a tool chain to compile your first compiler. That sense of bootstrapping. So I mean, to give you a very simple big picture idea, all the C compilers, C++ compilers that we know, let's say Clang, LLVM, Clang, LLVM together, GCC, MSVC, these are all written in C++, and they all compile C++. So that brings up the obvious question, how do you compile these compilers? And in the modern day, I mean, for the last 30 years or whatever, the answer is pretty simple. You just use an off-the-shelf compiler. Like when you're compiling Clang for the first time on your computer, you already have a C compiler or C++ compiler installed, so you just use that to build it. But back in the day, when the first compilers were evolving, when languages themselves were evolving, obviously C language itself has gone through so many changes over years, even more so with C++. You had to start from somewhere, right? And usually the answer is you write your first compiler in a different language. There were languages that came before C++. I mean, you could write a C compiler in Perl, which people have done, or you could write it in like a different language, like the Anthropic C compiler writes the C compiler in Rust. I don't think that's the reason for that is not because a C compiler is not available. I think that's a different design choice, but generally use a different language. And early back in the days, the only language available was maybe Fortran or something closer to the hardware like assembly. And that's what we'll try to do today. We'll try to sort of make a case or understand the process of how do you go from a very low-level language like assembly and build a full-fledged compiler from it. And we do this in steps, right? We don't right away start the best compiler you can write in assembly. That is a humongous task that no one wants to do. So we'll gradually build this. In today's stream, I'll write a bare minimum like a subset of C compiler, and then we'll use that in a later on stream to actually build a better compiler and maybe do another one in the future to do even more feature complete optimizing compiler. Let's see how that goes. But yeah, so today's goal is to spend 6-7 hours, how much ever it takes, to write a simple C compiler that compiles small programs. And the goal here is to have make it a subset of C, meaning whatever programs we compile, they can still be compiled with a regular C compiler. So we're not going to add new syntax. We're not going to change the meaning of any syntax. So on the side, we'll basically also try to compile it to the C compiler of the shelf one and check if the behavior is correct so that we can be sure what you're doing is right. Okay, so I haven't done any preparation for this other than just looking up some material in my head. And the one thing that I actually found which was very useful was this compiler called Sector C. Yeah, this one. This is an amazing project, by the way. I found this a few days ago, and this sort of like led me to go down this rabbit hole of trying to understand how assembly compilers are written, and this became like a motivation for this stream too. This is basically a C compiler written in assembly. This one is, again, x86, but this one runs in as a bootloader. So instead of like being a process that you run after you boot your computer, this is written as a program that runs directly when your hardware starts. And so it runs in short, in like 16-bit x86 assembly, but it's the whole compiler fits in 512 bytes of instructions and data. But I mean, data isn't like constant data, not runtime data. We obviously need more scratch space to work with. But yeah, and this compiler compiles very meaningful programs. Like this one generates a sine wave, animated sine wave on the screen. I think it's a really cool project. They have made some nice cuts and cutting corners in terms of the implementation to fit it in 512 bytes. Our goal today is not to try to keep the compiler small, but generally keeping it small means it's easy to implement. So we will try to do that. There's design choices in this one that we may not necessarily adhere to, but a lot of this is inspired from this. So this is a good project if you want to later read about. Yeah, so I haven't done any other preparation other than this. So we will start from an empty repository that I will just create, and we'll take it from there. So Let me create a new repository. Let's call it x86c. I think that should be good. Let's say an x86c compiler. And yeah, we'll be using 64-bit assembly, not 32-bit assembly, because obviously that's the most common one today. Okay, and then I'm going to clone this repository. I will add a simple git ignore, which I will copy from one of my previous repositories. Let's see, build swap, make this is good. I will start with the README. x86c. C compiler. I guess I should make this written in x86-64 assembly. Right, we will complete the rest of the description later, but see, this is good. Let's start with the source directory. We will also need, actually, yeah, source directory should be fine. We don't need any headers, includes, this is assembly. And I will start by writing a makefile. I usually like to include a makefile.inc where the end user can add more configuration options if they need to. And if the dash at the beginning of the include says, oh, oops, yes, you should be able to see the screen. And let me quickly make sure that, sorry, this, like I said, I've been a bit rusty. It's been a while. Why is my display capture not working? Sorry about that. There we go. Okay. Wrong screen though. There we go. Sorry about that. So yeah, what I was saying is I'm starting with an empty repository, just created an empty repository, and we just made a readme.md, just added a little empty source directory and made a makefile. What I'm going to quickly do is put this link on the website so anyone who comes here later can see it. Yeah, this is good. And then, okay, so we are starting with the makefile. Going to define some basic variables so that we have we can write the rest of the commands. So let's start with where this repository is currently located. So base directory tells you that. Then we will figure out the source directory from that. So that's going to be base directory /src. Then we will define the build directory. But what I usually like to do is I define it as $equal. So that way, if the user wants to supply a different build directory, they can supply a different build directory. And then it becomes /dir:/build. Right. And then what we'll do is we'll try to, as we write this compiler, there's going to be a bunch of different .s files that will be compiled together into a single executable. And they'll all be in the source directory, which means we need to have like a way to go through these files and compile individual of them. Make gives you gives you a bunch of options for this. So what I'm going to do is I'm going to define a variable called sources, which is simply going to say a wildcard over the source directory. But let's constrain it to .s files only. So what this is, I'm going to use capital S just as a convention. So it says I'm going to go through all the source files and pick the .s files. And then what we need to do is we need to define what all the object files are. And the easiest way to do that is to substitute the source directory with the build directory and then change the extension. So what I'm going to do here is I'm going to say source directory, comma, build directory, comma, we need to change the .s to .o. I think the way to do that is sources : .cpp. Give me a second. This is a little tricky. I think it's equal. I'm going to quickly look it up in my other, yeah, it's colon dot equals, okay, colon, so sources dot cpp colon dot s equals dot o. So what this does is it takes all the names in sources variable, replaces .s with .o, and then substitutes the source directory with the build directory. And what we're finally going to do is we're going to make our target. So the all target is the first target, which is just going to be executable. We also need an executable name first. So executable name equals, it's going to be build directory slash x86c. Oh, not 76, x86c. Okay, and then what we're going to do is we're going to say executable is going to be executable name. Right, and now we will define a rule to build the executable itself. So it becomes, actually I could skip this, honestly, this is getting unnecessarily annoying. Yeah, let's just do this. Okay, and then to define executable name, we need all the object files to be compiled. So we say objs, right? And we then need to give the actual command to compile it. So I'm just going to use GCC here. You can use any C compiler because most C compilers come with a built-in assembler and a linker. So yeah, again, we're using GCC, but that doesn't mean we're actually using the C compiler. I'm just using it to call the linker. The reason I'm calling it through GCC is because it will make sure all the runtime files like the lib start or librt is linked into, I think it's called lib start or something, which has all the initialization of your executable. And the other benefit of this is it will also help us produce an ELF executable, which you can directly run on Linux. We could go the complete binary route where I could just use GASM to compile it into a raw binary and then have some sort of like a separate loader for it. But for now, we're just going to use GCC or any standalone. I mean, I could just simply call LD2, which is the linker, but then the flags are a little bit long. So what I'm simply going to do is, let's say I need all the sources. So this is going to be dollar. Yeah. So this says all the dependencies, and then -o $@. What this means is call GCC on all the object files -o $@. And then we also need to provide the rules for how to compile each object file. And this can be simply done by writing a wildcard tool again. So I'm going to simply say build dir of %.o. So anything that matches this format, it first we need to say what it depends on. So it actually depends on, source dir of %s. So it depends on the respective .s file. And then again, I'm going to write the same rule. So in this case, I can simply still do this because there's only one dependency. If you just want the first dependency, you do this. But I can just use the caret to bring in all the dependencies. Yeah, and then it needs to go to $@, but then we use -c. Again, so I could use GASM here directly. I'm just using GCC. It internally just calls GASM. So we're not really cheating by using a C compiler. Okay, and by the way, feel free to stop me again at any point if there are any questions. I'm keeping an eye on the chat, but it's on the separate window, so sometimes I miss it. Yeah, all right. That's our basic makefile. I don't think we need anything else. Let's try to write a simple source file that says hello.s, which just defines the main function. We will change this again, obviously. And because I'm using GASM as just a executive choice here, it's a dialect I'm most familiar with. Not very familiar with assembly, by the way. I have written a decent amount of it, but I'm not a particularly I don't know how to optimize assembly too much, other than from the compiler side of things. So yeah, I'll be probably writing not the most efficient one, but it's a compiler that works. Okay, so what I'm simply going to do is for main, I'm just going to return here. And since we're following, at least at this point in this example, we are following the convention. So we will return in the RAX register, and so we'll clear it by saying XOR RAX. What this does is sets all the bits to 0, and then you return, so the variable is clear. And the one last thing we need is to tell it what section this belongs to. So I'm going to say .text, and .text says it's a executable section, which means the bytes in this section have execute permissions, readable permissions, but not writable permissions. Okay, and let's just quickly compile this and see if everything works. Okay, first of all, it says it can't create hello.o. Okay, yeah, so what happens is these wildcard rules need to be defined before they are used. So I think this should do it. Okay, let's see. Oh, it says no. Oh, sorry, I forgot to create the directory. So what we need to also do is make sure that the directory that we want to compile at exists. So we say mkdir, actually let's use this, mkdir -p. -p is a flag to say forcefully create it. If it doesn't exist, if it exists, don't complain. And then we need the base directory for this. There is a variable for it, if I remember. I'm going to just look it up. This is make rules. Yeah, it's that $@. So $d. Yeah, $d should give us the directory name. Okay, so this will make sure that the directory exists. And there we go. We have our first executable compile. I'm going to quickly run this, and it doesn't print anything. But it must have returned 0, and the way we check that is by printing $, which is 0, which is correct. Just to quickly sanity check this, we will also try to quickly modify it. Let's say, let's try to return 1. And run it, and this time we get 1. So okay, everything is working correctly. We are writing main, which means that we are actually all the entry points for all ELF executables are _start, but that is provided by the runtime library that GCC provides. That's what I was saying. Writing it starting from main is easier, but we could obviously also write that by hand. It just makes it easier. Okay, so we have a basic simple compiler executable running. We will start by, actually I should change it. So let's call that file driver.s, because that is the entry point for our function, right? Yeah. There we go. So what we're going to do now is go step by step. And this is where all our design choices will start coming in. So if you have looked at any compiler literature before, let's look at what the general flow for any compiler is, right? I mean, I can explain this too, but let's just look it up. So let's say parts of a C compiler. Let's say a flowchart, right? You can, by the way, I'm going to use Gemini as a reference material while writing this, just because it is easier to look things up. But I'll not be using to write any code. I'll be writing all the code myself. Yeah, so if you look at the workflow of a compiler, let's look at this one. So yeah, workflow for a C compiler, usually there's a source file, you have a preprocessor. Oh, this is too high level of a workflow. We need something slightly lower. I want something slightly lower. You know what? Let's just ask Gemini. Can you explain the parts of a C compiler, like the tokenizer, parser, etc.? Yeah, so the first step usually is the preprocessor. So the preprocessor is what takes all your macros and expands them, includes your header files and all sorts of other preprocessing that you can do. It's a language by itself. That's a very powerful language, but yeah, and this runs on your source code before. Actually, this runs after the tokenizer usually, so I'm surprised why they gave it in this order. So yeah, another mistake that Gemini is doing here. Usually the tokenizer runs first because the macros work on tokens, not on the actual source code. Usually the way it works is you run the tokenizer, you convert it, you preprocess it, and then some sort of like tokenizer again, because you might produce new strings which might need to be parsed. Actually, I'm not sure. Yeah, I think it just creates tokens to tokens. So there's a slight sort of out of order thing here. The first thing is usually the tokenizer, and then there is the preprocessing step that runs, and then you have a syntax analyzer or a parser. What this does is takes the sequence of your tokens. I'll explain what tokens are later, by the way, and convert them into some sort of a higher level representation that captures the structure of the program. This process is usually it's like a matching process that requires a grammar, like it's a context-free grammar that usually parses it. Not necessarily context-free for C, but generally it's meant to be context-free. And then you have some sort of like an analysis phase where you go and analyze the parsed code to make sure that it's correct, to figure out what optimizations you can do. And that processing is done on some sort of an intermediate language. There are different intermediates inside the compiler. You start with a very high-level parsed AST representation, which is like a tree of expressions and statements and so on. And then you lower it to something that's more like a IR or intermediate representation is more sort of focused on the semantics of it. So LLVM IR, for example, is an example of an IR that you can lower it into. And then you have an optimizer where you go and run a bunch of passes over the same IR. Basically, you take in IR, you modify it, and you generate more IR, and you keep on doing this till you're happy with the optimization. And finally, you have a code generator that goes and lowers it down to either assembly strings or binary executables or whatever you're targeting. And then post that, the compiler is done, but before you can actually execute it, you have the linker. Because generally when you write any C or C++ program, you write them in different translation units or different files. They all need to be linked together. They need to be brought together into a single executable that you can run. And that's the job of the linker. It literally stitches all your object files together. So yeah, so for today's project, what we're going to do is we're going to do parts of this, but we're going to simplify it. So obviously we are going to do a tokenizer, and I'll explain what a tokenizer is, but we're not going to do a preprocessor. So the first constraint of a language is no preprocessing, no macros, no hash include. It's a bare bone C compiler that basically just compiles the code that you send to it. So no preprocessing. And that's the first constraint I'm going to add to the website, saying no preprocessor. This includes no hash include, no hash define, no if def, if or if def, all the right. Yeah, that's the first constraint that we are adding today. We'll directly go from the tokenizer to the parsing stage. Okay, so I can close this for now. Let's go back to where we were here. Yeah. So what is a tokenizer? The tokenizer is a very simple process. What happens is when you write source code, it's a bunch of strings. It's a bunch of characters made into a long string. Now the issue is when you start to analyze the string and try to construct a program out of it, usually you have to go back and forth and sort of like match things, right? Like for example, say you have a variable name, like say foo, right? It's 3 characters, FOO. So when you're matching on some piece of code, you have to go and check, oh, if this, like, what is the name of this symbol, of this identifier? And you have to actually check 3 characters before you do it. And suppose you also have like other things in the mix, like you have keywords in the language. Like for example, while is a keyword in a language. Now, in the middle of the parsing, in the middle of like sort of constructing the meaningful program, you see WHI. Now, you don't know if it's while or if it's a name of a variable. Like it could be while x, which is not a keyword, but it's actually a variable. So it could be either. And you would have to completely match that before you know what exactly it is. And generally, this makes like going back and forth. Suppose you think it's like a identifier, like a keyword like while, but then you go ahead and then you see x. Now you have to go back and change the meaning of what you were doing. This becomes tricky, right? Your code becomes too complex. So usually what you want is a quick way to know what this current sort of like thing that you're looking at is. And the simplest thing you can compare is integers, right? Like integer is a simple equals comparison. You don't have to go and match multiple characters. You don't have to do like a mem compare or a string compare to know what this is. Integer is very easy to compare. So what tokenizer simply does is takes a bunch of characters that appear one after the other and then converts them into like a token. A token is basically just a number in most cases that you can directly compare and you can quickly compare. So you don't have to say if this character is W and the next character is H and the next character is I and the next character is L and the next one is E and then there's a space, then this is a while. You can just say is the next token while. So tokenizer just like chunks the string into simple objects that are like can be identified as an integer. And usually this process of converting the strings into tokens is it's a regular language, which means it's you can do it with a regular expression. Is the I mean, there's a more technical definition of what regular language is, but I'm not going to get into that. You can write a regular expression for doing this. What we'll realize is in most cases it's not very complicated. For a language like C, you can actually quickly recognize what type of a token it is with very simple checks, and that's what we'll be doing today too. One more important thing is the same sort of like source code, meaning program, can be written in different ways, and to sort of normalize that into a unique representation, we use tokenizers too, right? Like you could write a for loop with a space after it before the curly braces, or you could skip the you could skip the space, and they would mean the same program, right? Like what I mean is, let's say if I'm writing a for loop like this, for int x equals to 0, x less than 10, x plus plus, there's like so many ways I can write this. I could write this as this, like imagine all different like spaces removed and so on. I could also put this all in the same line. And these are like different ways of writing the same meaningful program. And what the tokenizer does is it converts it into a streams of tokens, so you don't have to worry about all these changes. And yeah, when you're doing parsing, you're just like, what's the next token? So that's what we'll be doing first. But which means before we write our tokenizer, we have to define what different types of tokens exist in our language, right? And so let's look at the list of like C language keywords that we need to handle, and make a list of stuff that we do actually want to handle. So here are all the C11 and 23 keywords. Let's not look at the C23 ones. Let's look at only the C99 one or C11 one. Let's look at the C11 ones. So we have stuff like break, case, auto, char, const, continue, default, do, double, and so on. The first thing we have to do is we have to restrict the set of keywords that our language supports. We don't have to support everything. For example, we don't have to support a for loop. We can just support a while loop, and you can still write meaningful programs with that. So let's make a list of all the keywords we do want to support. And this will also bring it, this will also restrict the kind of types we can support. Like for example, I'm planning to support the integer type given by the int keyword, and the long type and the char type. But at this point, I'm not planning to support the float type or the double type or the qualifiers like short or signed or unsigned. I'm not planning to support those. So that will restrict the kind of like programs we can write. In fact, the most important one, I'm not planning to support the struct keyword at this point, which is here, which lets the user define their own types, because you can still write programs by manually putting members together. So yeah, let's make a list of keywords supported, which will also give us a list of types we can support. So supported keywords. We don't want to support auto. Auto, by the way, in C means something different from what auto in C++ means. It's not really type inference. It is just auto, what's it called? It's like auto lifetime. It's like saying your variable is live only in the scope that it's defined. We can skip that very easily. We do need to support break, because we need to have some way out of a loop without having to like break it manually into multiple loops. A loop will usually have one condition, but it would be good to have another way to break out of it. So we will support, actually we will support continue as instead of break. So let's not support break for now, we can add it later, and there's a reason why continue is easier than break. Okay, so I'm going to skip case 2 because you're not supporting switch cases at all. We are going to support char. We are going to not support const. We are going to support continue, like I just said. We are going to support not for default. We don't need do. We're only going to support while loops, not do while loops. Double not required, else is required. We're going to support if then else conditions. Enum not required, extra not required, float, for, go to. If is required, yes, we're going to support if. No inline, int, long, yes. Null point register is also not required. Register is basically a type it's a qualifier? Oh, it's not a qualifier. It's I think it's an annotation that basically says map this variable to a register, and it's a hint to the compiler. Restrict not required. Return, yes, we do need the return keyword because functions have to return something. Short signed, size of we may need. I'm going to keep this as a token, but let's see if we need to handle this. Static not required, struct not required, switch, true, false, everything not required, union, unsigned, void. Yes, we do need void because we need a way to define functions that don't return anything. Although we could just basically write functions that always return integers, but it's good to have void as a return type. Volatile, while we don't need volatile. And that actually covers all of it. We're not going to support atomic, obviously, or generic, because generic is a keyword for the preprocessor language, not for the C language. Okay, and that's the list of our tokens. Right? And then apart from this, we need a few extra tokens, which is the identifier token. So the identifier token is a special token that says, hey, this is an identifier, which means this is some name, like a variable name like bar or main or foo. These are identifiers. So I'm going to like somehow identify it differently, but no. Sorry, my keyboard is kept slightly different because I'm sitting in a conference room, not in the place where I'm sitting. So my keys are, I'm hitting them a little different. Okay, so we'll support identifier. We will support integer constants, right? Because we need to have a way to define constants in our program. So those will be supported. Sort of day. Okay, and these are a list of keywords we'll support. So, oh, and we also need some special keywords, like we need function like parentheses. These are also keywords. They're separate keywords, by the way. We will also need the pointer dereference keyword. We will similarly also need the ampersand keyword. So this just this. We will obviously need semicolon. We will also need comma. So I'm going to put that in something like, let's just say comma. It's going to be hard to read. Yeah, I'm just going to say comma here. And then what else do we need? We need we need square brackets. So square brackets are mostly for array indexing. We are not supporting arrays at the moment, but we will support pointers, which do require square bracket. So we can, however, skip it for now because we will support the star and we are supporting all operations like plus, minus, and so on. So we can skip over that. So that gives us star, parentheses, comma is for function calls basically, and semicolon. And then we also need all our binary operators. So let's say C binary operator, binary and unary operators. You need all the operators, not bitwise. So I'm just going to say C operators. So we need plus, we need minus, we need multiplication, division. We could restrict some of these, but adding support for new operators is really not that difficult. It's just a matter of handling a specific case for a specific operator. We will not be supporting plus plus and minus minus because their syntactic triggers around equals 1 and so on. We will, however, have to support assignment. We will have to support comparison, all sorts of comparison. So let's say less than and greater than. I think that should be fine. We can combine the equals version separately. Actually, they're kind of easy. Let's say less than equals, need greater than equals, we need not equals. Yes, we also need just not. I'm gonna put the not with the unary operators just so that it's, oh, we don't need the star twice, the token is the same. Okay, I'm gonna put this here. I think that should be it. We'll add stuff later if needed. But yeah, oh, we also need curly braces for starting and ending of scopes. And that should be it for now. Okay, so with this, we also get supported types because we have restricted the keywords, which means we can only support a certain set of types. So we'll have char, int, long, and pointers. That's all we'll be supporting, which is fine. That's enough to write many meaningful programs. Okay, so yeah, you'll see there's no floating point types. For bootstrapping a C compiler, you don't really need floating point types because compiler internally never uses floating point numbers except for like some optimizations. Maybe you need some cost model or something, but you can always approximate it with integers and fixed precision. So yeah, that's what we'll support. Let's go to the website and quickly check if this is showing up correctly. Yeah, seems to be fine. Oh. Okay. Let's go and write our tokenizer now. So one thing that I was talking about is a tokenizer is a process of converting strings into numbers, basically. So we need to give each one of them a unique number, right? Like one way to do this would just be give them 1, 2, 3, 4, 5, 6, 7, 8, like char 1, continue 2, else 3, and so on. But if you notice one thing in all these tokens that we are seeing here is all of them are shorter than 8 bytes. I think the longest one here is continue, which is 1, 2, 3, 4, 8. Yeah, so there's exactly 8 bytes. The maximum sort of like keywords we have here are 8 bytes. The identifiers aside, the identifiers can be longer, but the keywords themselves are just 8 bytes. And what that means is the string, the bytes of the token itself can be our tokens. We don't have to like map it to a separate integer. We can simply say the bytes of char followed by 4 zeros is our token for char. And all we need to like have it defined in one place so we can compare it whenever we need to know if it's a particular character is char. So we don't have to specifically add new sort of like a mapping to the keywords. But we need to somewhere in one place define all the macros so we can define all the keywords so we can compare them later. So that's what we're going to do first. We're going to start a file called tokenizer.s, which the job here is to given a stream of strings, tell us what that token is. But before we write a tokenizer, let's just quickly also write the loading of the string so we can start testing the tokenizer out. So by the way, I was thinking of before I started the stream, I was thinking I would write the driver which loads the source file that you want to compile, etc. using C, and then just link it in together. But for the theme of this project, which is this is a bootstrapping compiler, so we don't have any existing C compiler. Let's try to do this also in assembly. And one of the ways to actually load a file is to call like fopen and read it, but that requires access to libc. Fopen, fclose, fwrite, fread are defined in libc. And we don't have access to libc because, again, we don't have a C compiler. So we will have to directly use the system call APIs from the operating system to call this. Now, technically, you can still call the read and write functions, and because they are provided by the runtime library from the operating system. But since we will be using very few functions, I will just write those manually in assembly by calling the system calls ourselves, and that will, because what we literally need is just open, write. I should just read, and that's basically it. So we and close afterwards. So let's just skip over all that and yeah, let's just directly call system calls. So by the way, we also need to allocate memory where we can store these read programs and where we can generate the code. And one easy way to do that is to pre-allocate chunks of data in the binary itself. So instead of having to call malloc at runtime and mmap at runtime, we will just reserve space in the executable in the data section to say, hey, I need a bunch of space where I can store some data. So let's ask Gemini what's the easiest way to allocate a bunch of zeros. So in GASM, how can I reserve a bunch of zeros? So this is the, we can use the resb directive. This is the most common way to reserve uninitialized space in the BSS section. While it technically reserves space, most compilers will default this space to 0 when program loads. Or we can use the db defined byte with a multiplier. What this says, if you want to be explicit and ensure that those zeros are actually written in the binary itself, not just in the RAM, you can use the data definition. So we do want it to be in the RAM, but not in the executable. We don't want to make the executable unnecessarily large. So you just want it to be reserved to be 0. What it says is the resb is initialized in the BSS section. However, most linkers will default this space to 0 when the program loads. We want to be sure that it's 0 though. I want to be sure the bytes are zeroed. But don't want to use up bytes in the executable. We can use BSS section. Yeah, so as long as we put the buffer in the BSS section, the loader will make sure that it's initialized to 0. So yeah, all we have to do is, you can use the lcom directive. What this says is just make a buffer of size 1024 under the BSS section, and BSS section is zeroed out by the loader. So yeah, what we will do in the same file, because we're loading this, it's part of the driver, I'm just going to put it in the same section. So we'll say section.bss, and then I'm going to say program source. Just going to call it program source, and all it says is just give it a size. So lcom we need to decide on a size. So we can support large programs, but for now, let's say we support 4 kilobytes of source code. That's plenty. Or yeah, we can just make it 40 kilobytes. So it's 10 pages. of memory. That's plenty for most of the programs that we'll be compiling today. We also need to know how large the program is. However, since we are zero initializing the whole program, we actually don't need to know where it ends. The moment you see a 0, that means the program has ended. And that's part of the reason why I wanted to zero initialize the buffer. I could leave it uninitialized and manually put a 0, but this is just easier. Okay, so the first thing we need to do is to load the program. And the program would be, the name of the file that we want to compile would be sent to us as an argument to the main function. And the main function, if you remember in C, gets 2 arguments. The first is the number of arguments, and the second is a list of the actual arguments, a string. We will, since this, at least at the entry point, we will be following the calling convention of the host operating system. So in this case, it's Linux, so system v. Oh yeah, thanks for joining. Obviously, yeah, I'll be recording this thing so you can watch it later if you're interested. And thanks for engaging, and thanks for letting me know when there were issues with audio and video. Okay, so let's open the file and load the program. So we only have the system call interface going for us. We first just let's get the name of the program. So we'll have to look at the calling convention that the host operating system follows, which is system v. So I'm just going to look up system v abi. It should be under x86 calling conventions. Here we go. Yeah. So what this says is the arguments, the first 6 arguments, the integer or pointer arguments, are in RDI, RSI, RDX, RCX, R8, R9 respectively, and then the rest of the arguments are on the stack. Our program main function only has 2 arguments, so the number of arguments would be in RDI, and the actual string arguments would be in RSI. And the type of this RSI is a pointer to a pointer. So what this means is, if we take RSI, it is going to be an index into a list of pointers. So what we will use RAX as a scratch register. By the way, RAX and RBX, because those, I mean, we just define our own convention for the rest of this program. So let's start by taking the string that holds the name of our file, which is going to be pointed to by RSI of 8. So what the syntax says is RSI of 0 would be the first pointer in memory, and RSI of 8 is the second one, because pointers are 8-byte on the system. And then we're going to move it to, just use move q to the RAX register. Since this is GASM, the left-hand side is the source, and the right-hand side is the destination. So now we have a pointer in RAX that holds the file name. We then are going to call the open system call. So let's say Linux system call list. Need open. Yeah. So open doesn't. Yeah, so system calls, by the way, follows a similar ABI. I mean, the register order is different. Wait, this is 64. We need a 64-bit system call. Yeah, so it follows a similar ABI, except for the RAX register holds the system call number itself. So what we need is to call the open system call. It takes 3 arguments. The first is the file name, the second is the flag, and the third is the mode. We look at what this means separately. Yeah, it's given here. So mode and flags we'll get to later, but first we need to move the system call number into RAX. And we need to move the name of the file in RDI. So let's honestly just change this to RDI, so we directly have the file name in RDI. And then we're going to move the constant 2 into RAX. So this is system call number 2, which is open. And then we need flags. So let's look at what flags are. these are basically status flags to say what mode you want to open the file in. I think we can just leave it to 0. Sorry, we just need yeah, flags we can leave it as 0. Modes will tell us whether you want to read the file, write the file, and so on. So we need the constant values for this. We can't use the macros because we're writing in assembly. We could include the headers. There's a way to do that, but we will just look up the constants from it, and that should be fine. I think they should be defined under fcntl.h. So let's try to see if we can find it. User include. No, it should be under just include. One of the easiest way to find where these files are located is you can simply write a keep a scratch file, scratch pane here. Where's my shift broken? What's happening? Okay. Huh? I think one of my shift keys is stuck. Okay, sorry, that was a little annoying. Yeah, what we're gonna do is just include the files that we want, and we can ask the preprocessor to tell us where those files are. So we need stat.h fcntl.h, right? And that's where it is. And what we're simply gonna do is just preprocess this file. Which will tell us where the file is. It's under user include fcntl.h. Let's look for o underscore read only. What is it? rd only. Okay, it's not defined. It should be defined here. It might be under bits fcntl. You know what, we're just going to go here and search for o underscore rd only. It's defined under ASM generic here. It is defined as just 0, so we can move this to 0. Okay. That was easy. Okay. So the modes, the flags are zeros and the modes are also zeros. So we just what are the registers for it? RSI has the name of the RSI has the flags, and RDX has the mode. So we just zero out both of them. Perfect. So we have our system call is ready, and then we can just do syscall. What this will do is basically hand over the control to the operating system. The operating system will load, open the file for us, and the output then arrives in RAX. The register, the return value is always in RAX. So at this point, we should have a file descriptor pointing to the file that the user has asked. Now, obviously, we should assert and make sure the file actually opened. So that's what we're going to do. We're going to make sure that the convention says that the return value is the file descriptor, and if there is an error, it will return a negative value. So it says open and create, return a new file descriptor, or -1 if error occurred. Right? So by the way, we are going to also now create a generic like error function that we can use to report error at any point, and this will like help us debug most of our implementation as we go on. So what we're going to do is we're going to compare RAX with 0, because if the value is negative, it means that the file descriptor that we got is wrong. And then we're going to say jump on less less than equals, because I mean, I guess 0, we can just do JL. So it says if it's less than 0, then jump to report error, right? We need to follow some convention for what the error would be. So I'm going to define some constants again. So in the data section, we're going to say file not found. And we're going to describe a string here that simply says file not found, to have it zeroed out. And we need to have some way to report this error. But for now, what I'm simply going to do is report error is going to jump to report error. So this will basically go into an infinite loop that we can then debug by attaching a debugger and do it. We can have I mean, I could simply write the write system call here that will print it out to the output, like standard output or standard error. Honestly, we could just do that. Yeah, let's just do that. So let's have a reasonable error reporting mechanism, so this simplifies things later. We're going to use the write system call for this, which is syswrite 1. It takes the file descriptor in RDI buffer and then count. We just need a way to know the count for this. There is a way to do this. GSM, how do I get the length of a string constant? You basically put a marker after that and you subtract them. That's what you do. Yeah, so you can basically use you can like define constants before and after, and then you can take the difference of them. So we could like do it this way. Right, and then we can subtract them to know what the length is. So we're gonna follow a simple, for error reporting, we're always gonna follow a simple ABI where we put the error in RBX and we put the actually in RCX and RDX the length, and that way we can just call jump error. So for report error, we're going to move file not found actually let's use LEA here because it's a pointer, it's easier. File not found into RCX and file not found underscore n minus file not found into RDX. Okay, and if it's less than, then we do 0. Move and LEA don't affect flags, so the flag should still be correct. And yeah, and for the report error, what we're simply going to do is call the write system call. We need to know the std error file descriptor. We're just going to Google this std error file descriptor number is usually 2, so we need the system call reference. Move q $1, no, write is 1, yeah, into the RAX. We need $2 in file descriptor, which is RDI. Then we need to move the RCX, which contains the string that we want to print, into RSI, and the length of that string into, oh, it's already in RDX. Perfect. We don't need to do anything about it. We could also change the convention to be RSI, but no, it's fine. It's actually, no, we need to shift it anyway, so it's fine. Yeah, so we have set up our arguments, and then we just say syscall. At this point, we can just jump back to report error, And the reason for not exiting and immediately stopping the program is so that we can attach a debugger and then debug what went wrong if this happens. Because this is going to happen a lot. We're going to have errors all throughout our programs, and it'll be easier to debug it this way. So what this is simply doing is reporting that error that we have. Okay, and at this point, if everything goes well, the file is open. We're going to test this quickly. So I'm going to compile this. Obviously, there is some errors. Line 4. %x. Sorry, this is. How did this happen? Oh, I think it's just ASCII with no double I. ASCII is for a string. ASCII Z is for saying we need a 0 at the end. Data cannot be used in making. So what's happening is it needs to compute the differences here. It doesn't want to. Actually, we can define this in the text section because it's a constant anyway, right? Yeah. Let's ask Gemini how to move this. I can just define it here. Okay, so instead of doing this, let's just say len equals dot minus file not found, and then we can just do file not found underscore length, right? Oh, it says you can use the EQU instead of using. Okay. Okay, so now we have a true constant defined here. T should probably be at the top. Yeah, so all the error messages go at the top, and I think this should be good. No. Which relocation is it complaining about? This is not a relocation anymore. This is also not a relocation. I'm going to just comment out a few things and see if that goes away. Nope. Maybe it's this. No. Maybe it's the program source being loaded. No, we haven't touched the program source yet. Interesting. What is the relocation about? The linker is complaining failed to set dynamic section values bad. Right, okay, I'm going to comment out a few things. This is not an issue either. Oh, it's in the tokenizer? No, it's not in the tokenizer. Text cannot be used. I'm just gonna ask. Yeah, I think we have just, but I'm not trying to load any constants here. I'm not saving this. I'm saving this. Okay, I'm gonna comment this one out for now too. Nope. What is the relocation? Wait, is colon? Oh, here. Nope. This was working before, right? No. Okay, am I making... Is colon not comment? Oh, it's bound, of course. Okay, that was silly. Okay, let's... This should work. No, okay, so there's a relocation issue here. This is gonna need RIP. So it's going to be RIP. Okay, perfect. This works fine. You can jump now. Sorry about that. Okay. Okay, perfect. So we tried to open the file and it failed. So we should, since we didn't provide any parameters, we should also check if the parameters exist. And so we're going to define a new error for that. File name missing. Okay, this is good. Now we're going to compare RDI, no, RSI, where the RDI, where the first argument is with, you need to have at least 2, right? Yeah. And if it is less than 2, we'll first move the errors. So we say x jump on less than 2, yeah. Just going to compare. Just going to compare. We can actually just compare EDI because it's an integer argument. Wait, what? Oh, sorry. It's the other way. My bad. Okay, this is good. Oh boy. we have our first issue, so I'm going to simply attach GDB and step through this. Okay, so at this point, let's see what our EDI is. It is 1, which is less than 2. Next I, next I, and it's like vaulted right away. Oh, forgot the zip constant. I printed some error, but that doesn't seem right. Finally missing len, which was correct. Oh, it just kept repeating, so we need to report error loop. Oh, I'll keep repeating the error. Okay, there we go. We have our first error message. We should also put /n. Right? There we go. Okay, so let's invoke it with the file name now. In the empty.c, we're just going to define one function, which is just int main, return 0, just this function. Let's try compiling this. And something happened. No more errors, which means the file must have loaded correctly too, but we need to make sure that it's correctly loaded. It's just a file descriptor at this point. Let's also load the file. So next we can do the read system call that will load the file from the file descriptor into our buffer. So we need to use the 0 system call. It takes file descriptor, RDI, buffer, and count. So let's see. We do move q rax into RDI. We do $0 into rax, so system call number. We do, it needs just the buffer and the count, so we can do leaq program, what's it called, program source. RSI, and then $4096. So we need to leave at least one byte to be not loaded. So I'm going to do 409, instead of 40960, I'm going to do 59. So we have at least 10 at the end into RDX, and then syscall. Okay, so what will happen here is the program will be loaded in our buffer. So we can make sure that this happens by invoking our compiler with GDB and just stepping through it, right? Let's put a breakpoint on main, run. And at this point, we should be able to debug it. So we can say print as hex program source. So it's not a label. It's yeah, we didn't compile it that way. So what we can do is there was a buffer where we loaded, right? So RSI must contain what the buffer is. So we can try to check that first. Yeah, it has the address of our buffer. So we can simply print bytesat. So we could do print char star $RSI. And there we go. It has our program int main /n/t return 0 /n/n. Perfect. So we have loaded our program. We just need to close the file descriptor now and start working on the tokenizer. This has taken a long time, but we will get there. Okay, let's just close the file descriptor. The close system call is 3. Just take the file descriptor, and that's it. So the file descriptor was in RDI. Oh, it's already in RDI? Yeah, perfect. So you simply need 3 in RAX and syscall. You don't need to check the return value. Close is guaranteed to succeed, if I remember correctly. It does fail, but that's fine. We'll ignore the errors when close fails. Okay, so now we have loaded our program. We need to start tokenizing it. And one of the constraints that we're going to do is to make our life easier, in the beginning at least, we're going to say that all our tokens are separated by a space character. And this is easy because we don't have to like think about combined tokens together. If it's like a special character, it just becomes a token by itself, but identifiers, names, just easier to identify if they're separated by space. So I'm going to modify our Scratch program to make sure that that is followed. So we have this. So this is the, at least in the beginning, this is the program we'll compile. I will change it later to handle programs that are not separated by space, but and by space I mean anything that's like white space. So single space, tab, all those new lines, they're all considered as space. And there's a very easy way to check that. So okay, we have our basic program. Let's write the tokenizer. So this will go into tokenizer.s. We need a buffer where we will output our tokens right now. When we change this, the tokens will not actually be stored in memory. They would just be called on the fly by the parser. So we don't actually need to dump them somewhere. Typically, like the tokenizer and the parser are fused together. So as it gets tokenized, the parser immediately parses it. But we, for debugging purposes, we'll be first dumping all those tokens into a buffer, and then so we can look at them and make sure that it's correct. Okay, so let's start by defining a append token function, which will, given a token, add it to a buffer, right? And this needs to be exported. So yeah, append token. And so just like we made a program source, we're also going to make our token buffer where all the tokens would be kept. So let's say this is great. We're also going to define a simple like variable that holds where our end of our token is, because we want the append token to be sort of like self-contained. So we're going to say 4 bytes for that. Actually, let's just do 8 bytes, so we can just keep end of our token. But it needs to be initialized to, let's ask Gemini. How do I define a variable with of 8 bytes that is initialized to the address? You can just put the quad of another label, so we don't need lcom. Just say quad, and you say token buffer, right? Yep. So this token end will have the address of token buffer. And so now what we can simply do is append token would, we're following a convention where, we're now following an internal convention where RDI, RSI would still contain the first 2 arguments, and we'll try to restrict it to 2 arguments. We will not try to go more than that. Yeah. Actually, no, sorry. We're following the convention where Um, RCX, RDX are the first two arguments, my bad. Yeah, RCX, RDX are the first two arguments. We'll write this down somewhere. Following conventions for x86c. R1 in %RCX, R2 in RDX, RAX is return value, return 2. Some of the functions will return a pair, like for example our tokenizer, so they will be in RBX and RCX, and we will be using R10 onwards as Scratch global variables in R10 onwards. So these will be sort of like variables that are live across the whole project, and they will contain like some state of the parser, some state of the code generator, and so on. So like for example, we'll store where the output program is being written in one of these registers, so that way we don't have to keep loading it again and again. Yeah, and we also need a few more arguments. Some of our functions might take more. Let's say RCX, RDX. I don't want to use RBX because you're using it for an RSI, RDI. Could use. Honestly, it's just easier if we follow the system we calling conventions. You know what? Let's just do that. It's fine. So what? RDX, RCX, yeah. Which means we need to change our error functions too. So I hope it's not corrupted. This should be fine. And the yeah, this seems fine. But here the RSI is corrupted now, so we just need to make sure that the RSI is stored somewhere. Yeah, we're designated RAX and RBX as local scratches too, so gonna put it in RBX, that this way it's not corrupted. And then RSI, RDI, RSI are fine. Clearing it out, just call RSI. So report error 1 into RAX, 2 into RDI, but before we 2 into RDI, we do so the first argument goes into the second argument, but before the second argument we need to move it, so RSI goes into RDX, RDI go into RSI. This should work, right? Yeah. Okay. Great. So we have append token, which would get the token in RDI, and that's it. So we're just going to, it's an 8-byte variable, so we're just going to store it. So move u RDI into, we need to load the address first. So token in, it's a value, so we're going to move token in of RIP into RAX into array x. So storing it at that location, and then we're going to shift the array x by 8. And store it back. Great. So we have a simple function that appends a token into the buffer that we have. Now we need to start writing our tokenizer. We need to implement one function that says get nox token. Right? This will get a token from the program source. This also means we need a way to keep track of where we currently are processing. So we're going to say program source end. This will be initialized to program source. So this needs to be in data, right? So get token will always look at program source end. Let's say program source or token head. Yeah. Okay. So now we have the actual get token function, and we'll follow a very strict sort of like ordering to make it easy to parse. So let's look at the ASCII table. It's an easy one. Yeah, okay. Oh wow, some random website I'm clicking. Okay, this looks okay. What we have here is a list of characters and their integer values. We'll notice that below 32 everything is special characters which we can treat off as space. So if we see any character below 32, including except for null is an end of the program, so that's where we stop parsing and we stop compiling even. But everything between 1 to 32 is basically a space character for us. So we can say that's the end of our tokens. From 33 to 47 are a bunch of special characters which are part of our token stream, except for which are sort of our special tokens, except for the curly brackets at 123 and 125, which we will handle separately. And everything in between from 48 to 57 is again integer constants. That's why we'll start parsing integers. And then 65 onwards is 65 to, I'll have to break it again because these cannot be part of identifiers. So yeah, so if we follow a strict hierarchy, like ordering of parsing our tokens, types of tokens, it will make it easier for us to like not have to add too many conditions. So the first simplest check we'll do is, the first thing we'll do is load a character, right? So we will do move q, what was it called? Token read head. So token read head of RIP into, we also need to, we need to do the same treatment as the append token. So we'll do move byte. In this case, we'll just do a move byte of array x into rbx, and then we'll do this. Can probably be optimized by keeping the token read head in a register, but for now we'll do it in the, actually maybe, you know what, because it's going to be live the whole duration, we're just going to define R10 as the token read head. Okay, which means we don't need to move this. We can simply do R10, and it's job of the caller to make sure that this is done correctly. So the driver will move token read head. And we actually don't need token. We will need this space still, because in case we have to ever spill R10 somewhere, we would need to allocate some space for it. So I'm just going to keep the token read head, but I'm going to simply just move program source into the register. So LEAQ program source of RIP into R10. So R10 will always, for the entirety of a program, hold where the current next token start is. This will make our tokenizer much easier. Much easy. Okay, so we have get token function, which now just moves a byte from that into register and then increments R10. Perfect. So now we have our token. We first compare if it's the end of our program. So we simply do cmp rbx rbx, right? So this is just compare. We should compare BL. Since it's a byte now, let's just use BL, and then we'll say jump on 0 program parsing end, and program parsing end is defined here as just a loop. Why am I writing C in the middle of this? Great. So if you reach the end of the program, we have we're done parsing, but then we have to check for end of characters. So this get token will be running in a loop, by the way, so that will make it easier. If we ever see the end of actually, we don't need to look for end character, because so here's the problem. Between multiple tokens, there can be multiple spaces. So we need to skip over all the spaces that we see. So if there are any spaces right in the beginning, we can skip over them. How do we implement this? So we have to decide whether the spaces between tokens should be consumed by the previous matcher or the current matcher. Actually, let's just assume that all the spaces are eaten up by the previous call to get token, and this means we also have to make sure that when we start the program, we're starting from the first character, not from a space. Okay, so we can simply check for if it's like at the beginning of the token, it cannot be any of the spaces. It has to be one of the special characters or numbers or so on. So let's first check if it's less than 47, because 47 is a special character. So we'll say comparison of BL with 47. Let's do 48, so we can do jump on less than. So if we see anything between 33 and 47, we jump on less than get, let's say, what do we call them? Get operator or get special character, right? Give it a proper name actually. Get token special character. If it's between 0 and 59, sorry, 48 to 59, I mean in this case 58, then it's an integer. So we say compare, we already compared against 48, so we just need to compare against the higher bound, so it's going to be 58, yeah. BL jump less to get token integer. So the simple logic reasoning here is, if the token starts from an integer, it is a integer constant. There is no other way, because identifiers cannot stop with numbers. They have to start with a special character, with a letter. So great. Wait, is underscore included in that? No, underscore is, because underscore can be part of it, of name, so we can get to that later. Yeah, so 33 to, sorry, 48 to 40, 58 has been handled. 58 to 63 again is operators or special characters. So let's say compare, how much is it, till 64. At the rate is not a special character, so you're just going to ignore that. Jump L to get token special character again. Yeah, this is why we are sort of breaking it down into cases. That way we can write them separately. And then we have 65 to, what's that, 90. So we're just going to simply compare against 91. And the reason for this is there is a at the rate in the middle. We're not checking that. We're not checking that, hey, is this like, this would be an error. If you ever see at the start of a token, it's an error. So we're not going to report that because that requires writing a lot more checks. That brings us to another constraint that we have in our language, which is bad characters not checked, like at the rate. We can fix this later. We can go and add more checks later, but I'm going to also start putting comments on this. What character it's checking for my. Again, not all of these are meaningful, but we are checking them because some of them are special characters. Percent single quote parentheses, close parentheses, star plus comma minus dot slash. Colon, semicolon, less than, equals, greater than, question mark. The rate is skipped, so it's fine. And now we're checking A to Z, right? C is up to 90. Identifier, right? And then we have some special characters. So we're gonna skip square brackets, carets, underscore. We also need underscore. So we're gonna say, actually, yeah, underscore needs to be included as part of special characters too. But because none of these middle ones like square brackets, slash, carets have any meanings, we can just directly go up to Z. That way we don't have to check for special cases. Like these will just be included as part of the special of the identifiers, but that's okay because we're not reporting bad characters. So we're going to say up to 123 directly, and that will check all our capital A to small z, everything is included in it. There's no special characters that we care about in the middle. In the future, if we add for square bracket, we would change this to change when supporting square brackets. And then finally, we have curly braces, or and curly braces, all of which should be included. So we will have comparison of, this is what, 126 GL get tokens special character. By the way, some of these tokens in special characters, most of them are single characters, except for things like double equals, not equals, and so on. We will handle them as special cases within the the branch. So if it starts with a or, we'll also check if the second one is an or, and so on. So we'll handle like the double one specially, but they'll only handle uh, like all the special characters will sort of be merged together into a single token, which is what our space delimiter does anyway. So like if we have double equals, there won't be a space in them, so they would get merged into a single one. Okay, so now we have handled different types of tokens, and the reason why they're different type is some of them have different logic. For example, the identifier one specifically, they might need to like the way we create the token is different. Like we don't create a separate token for each identifier. We have one token type for identifier, and then the actual token value will be in some separate register. And to support that, we will make sure that it's like handled differently. Not all tokens are passed in the same way, or created in the same way. Okay, so let's start writing all these cases. We will have, there's no fall through here. There shouldn't be a fall through. One of these should be true. So we will simply say special character get token special character. Okay, now we start. This doesn't need to be global, it's a local function. We say for special characters, first of all, the character we have just picked up is in BL. We are going to follow a convention where tokens are assembled in a register, and we will be reserving one of the registers for that. This makes it easier going forward. But within the local to the function, we will assemble them within RAX, RCX, and RDX. Like we will have to use some local variables. Why did I use RBX here? Why didn't I just use RAX? Is there a reason for that? No. You know what? Let's just change this. Sorry about that. I'm gonna quickly change everything so things are a little more consistent. Great. So we're going to assemble the tokens in RBX. So the as we keep parsing each character, it's going to be shoved inside RBX. If it needs to be longer than RBX, it's going to RCX into RDX, and finally into R. We don't need to call any functions in the meantime, so RSI. Yeah, RSI should be good. So what this means is our tokens will sort of like get filled into these 4 registers, which also means that the longest identifier we support is going to be at most 32 bytes, because we're not putting the identifiers into strings, we're just collecting them into the character. And if like, yeah, so we don't want to like keep on filling the string into memory. We'll just say that maximum identifier length is 32, which will now go on our website. Maximum identifier length equals 32. This also means the maximum integer length is 32, but since we're only supporting decimal values, that is kind of implied. Like 32 decimals is a pretty long number. Okay, so what this also means is before we start parsing, we need to clear all these registers. So I'm gonna clear them. And RSI. Perfect. So before we start passing in a token, all of these will be set to 0. Now, within each we need a mechanism to quickly put the characters into the registers and shift them. So let's see. Maybe what we should do is as soon as we read it, we put it in the register. We'll have a read till end function. Okay. So what we're going to have is we're going to make a special read till end function, which will keep on reading into the character, sort of like stream till we see the end of a token. So what this read till end will do is it will first put the byte that we currently have in the accumulator into the register. So we also need to keep track of how many letters we have read so far within the current register. My plan is to unroll it anyway, so this shouldn't be a problem. We need to know how many registers do we have, how many values do we have. So we need a register for saying what the length of the current token is. I wish we could look at the tokens and just know. Actually, yeah, since we can never have a 0 byte in a token, as long as the highest byte is 0, we don't need to spill. I mean, we don't need to shift. So yeah, I think this is fine. The highest byte of our RBX register itself tells us if that RBX register is full and we need to shift. Okay, great. So first thing we'll do is we will check if that registers need to be moved. So we'll say comparison. We need to create a constant that's checking the highest byte. So this will be $ff 0x 000000. This is 4. But we can't really compare. This needs to be moved to a register. Oh, this is annoying. I'm gonna ask Gemini what the best way to do this is. How can I check if the highest byte of my register is non-zero without modifying it? Yeah, I'll have to use move ABSQ. Not a highest, but I will check. Yeah, this is the only way. Okay, we'll use. Do we have the scratch register left? We don't. So AL contains the token that we have just loaded. Actually, before we jump, we can just, yeah, so read till end can assume that RAL is free. And the way we can do that is before we do all the comparisons, since at this point we know that RBX is definitely free, we're just gonna do move AL into BL. The lowest byte is already in BL. The first token is already moved. So at entry of RBX, you can always assume that the RAX is free. So now we can use this to compare. We can say compare. No, we need to test Q RAX RBX. If it is non-zero, so jump on non-zero. We say shift and continue. So what shift and continue is going to do is it's going to move the values that we have read so far one register up. Right, so how do we move this? We have the order is RBX, RCX, RDX, RSI. So RDX turns into RSI. rdx goes into rsi, rcx goes into rdx, rbx goes into rcx, and rbx is clear. Yeah, so, and this can simply fall through to read till end again. Yeah, and because rbx is free now, this won't happen, so we are good. So read till end, what it simply does is, like, you're just going to consume all the tokens that appear till there are spaces, and those will just be added into the register. And for tokens that are like identifiers, they'll always be, sorry, the tokens that are keywords, they will be in rbx only because the tokens are small, short, we don't have long tokens. Okay, so this will, now we need to actually read the character. So what is the register? R10. So we do move q, no, move p, R10 into AL, load the register, we quickly increment R10. Okay, so we have read a character, we need to first check if it's a special character or end. So we say compare so 0 is a special case. Did we compare 0 here? Yeah, we did. Say jump on 0, we go to, what is it? Program parsing in. Okay, and otherwise we check if it's less than, what is it? Less than 33. So if it's less than this, we just do read it till end. Right? Now, what this is essentially doing is it keeps on consuming characters as long as it sees a space. If at any point we don't see a space, which means we have already read an extra character that we shouldn't have read before, we put it back. So we do, and we can then return. Right? This read till end is the end of our get token function anyway, so this will return from here. And at this point, our tokens are stored in rbx, rcx, rdx, or whatever. Like the sequence of tokens are stored in this rbx, rcx, rdx, rsi. So now for special characters, we simply need to call this. We just say read till end. Because it doesn't matter what the characters are, as long as there is no space, we can merge them all into a single token basically. So get token special characters is very easy. What was the next one we were supposed to write? Let's do identifier next. Actually no, let's do get token integer next. Should we limit the number of integers lengths we can have? Let's see what int max is. In decimal, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it can be 10 characters at most, which means we'll have to look at the second register if needed. Actually, integer handling will be done separately. We won't parse the integer using strings. We'll have to like actually convert them to integer values. So let's do identifier first. Okay. Get token identifier. So with identifier, what we're going to do is it's a little tricky. So it's not going to just be put the identifier name into these registers. We'll have to actually put a special value in the RBX register, which says that, hey, this is an identifier. And in RCX, we will actually put like the name of the identifier. And the way we'll do this is actually dump the name into a symbol table and then put the index into the RCX. So that way the user doesn't have to like we can now compare if the identifier matches by just looking at RCX. You don't have to like do string comparisons in the middle of parsing. We can simply just say, oh, is the index into the symbol table the same? If it's the same, then these are the same identifiers, and that makes things much easier. So yeah, let's just let's implement get token identifier. So the first thing we need to do is read till end. But at this point, read till end is not going to return back after the token because we still have the movement around to do. So what we're going to do actually is to call read till end instead of just jumping to read till end. And that's why the control comes back to us after we're done, and we can return from here. Now we're guaranteed that all the space characters have been eaten up. The whole identifier has been moved into RBX, RCX, RDX, and so on. Now what we need to do is first dump this as it is into the simple table. So we will now have to define a symbol table, which can go after this. So in the dot section dot bss, we have symbol table. Actually, let's call this identifier table because the symbol table is actually separate from the identifier table. This is just a way of converting strings to integers. There's a separate buffer which will actually keep track of which variables are live and which functions are live. That is different. So this goes, this can also be 40960, 4 kilobytes. We need an end of the identifier table. So I'm going to say identifier table n, and this we can keep in memory. We don't have to actually put this into a register because this is very like not accessed as often. It's only when the identifier needs to be dumped. And so what this is going to be organized as is 32 bytes per identifier. So it's like 32 consecutive bytes are each separate identifiers, and we just need to now like dump them. As long as we follow the same convention of dumping them, we should get like the same meaning. So get token identifier has passed all the registers. Now we're just going to move them into the registers. So first into the table. So we first load the end of the identifier table into RAX because RAX is free. Is it identifier table of RIP? Okay, and then we are going to one by one store them. So we will say move RBX into RAX, RCX, RDX, into 8, 16, 24, and then we can simply do cube 32 RX, and we can store it back. Right, so what this has simply done is dump the identifier as it is into the identifier table, and now what we need to do is we also need to like shift the identifier index into RBX. So if we actually we need to subtract like the current end of identifier table end with from identifier. So we need to do, we already have the end of identifier into RAX. We need to move the start into RBX. So we'll say move Q, LEAQ, identifier table of person RIP into RBX sub Q RBX comma RAX. No, RAX comma RBX. Right. So this gives us the index into the table. We should shift it, right shift it. Is it LSR? Need to shift off 5 bits, right? SHRQ shift, right? Yeah. RBX. And this is our identifier ID now, so we can move this to, to tell it how much. So $5, yeah, 5 bits. So we're shifting off the 32 byte size of it. Okay, yeah. So, and then we move this into RCX, right? No, get token returns the token in RAX, which means this also needs to go into RAX. So read till end actually needs to move QRBX into RAX. We need to make sure that the register is fine, the token is finally into RAX. But in this case, we will have it in, we already have the identifier in RBX. We just need to move the special token number into RCX, and we just need to choose a value for it. So Q, we'll define some constants. Yeah, there's also hash define. Let's just use hash define. But it's only specific for GCC. If you're gonna later move to GSM, okay, let's just do EQU then. Let's just call this special tokens. So token constant. So yeah, this can simply be so token number 1 can itself be identifier, because 1 can never be a special character since it's a space. So you can say it's 1, and then for EQU token integer is going to be 0x2. So yeah, we have special characters, and rest of the tokens are their string itself makes them a token, so we don't have to worry about that. We will eventually have to write it down though, because when we write the parsing code, we'll have to like have a handy way of comparing them, and we don't. Yeah, we'll add these later. Okay. Great. So now we have our identifiers dumped into the identifier table. The index is an RBX, and we just need to move the identifier number. So we say token underscore identifier into RAX, and we can return. So here we have followed our calling convention of return values being in RAX and RBX. Generally, most of our functions like get token outputs will be looking at only RAX, because that's just a token number. But if it happens to be 0x1, then it will also hold the token index into the in RBX. And we need to now finally only implement get token integer, which is similar to the identifier, but instead of having to so right, so we won't use the read till end function here, mainly because we don't want to like create the string in the same way. We need to use like the binary equivalent of it. So we'll have to use like multiplication by 10 instead of shifting by 8. Oh, by the way, I forgot to put anything into the register. Did we do that? Yeah, I just retail never reads anything. Sorry, we forgot the case where oh, this was consuming spaces, my bad, this was wrong. So if it's less than 33, we jump to, sorry, this was wrong, consume spaces, right? Yeah, if it's the end of the token, then it's, and if it's anything more than 33, which is not the space, then it needs to be appended into the token. So the way we are appending it is, yeah, sorry, this was bad. SHLQ. We get first left shift the register RBX. I guess this is where we should check if it's full. No, this was fine. We can check it right away. So we move RBX to the right by 8 bits. And then we just OR it in. So I would just add it too, because yeah, I think this is fine. You can just okay, this is good. So yeah, in fact, we want the move behavior. So we shift RBX and then we move AL into it, and this will actually keep the thing and it will go back, and we need to now implement consume spaces, which will, right, and after this we need to go to read till end, keep on reading. Eventually we'll see a space or we'll see a program end. Actually, so if it's an end of a program, we just can't go to program end, we have to actually return okay, this needs to be changed. I'll change this. Consume spaces, we'll just go and consume all the remaining spaces. So this will do same thing as this. If it is And at this point, if it's anything else, then we do dqr10. Yeah. Move q rbx rax with q. And for this one, we have a label get token end. So this can simply go to get token end, and so can this. Yep. Okay. So what this is doing is we move the registers, we get the next character. If it happens to be 0, then you just say we're done. If it is any space character, then you go back to consuming spaces. If it's not a space character, we go back because we've read an extra character, and then we go to token end. Okay, this seems correct to me. Yeah, we don't need a DQ here because we've already reached the end of the program. There is, actually we should, because next time this gets called again, it's going to try to read. We want to read out of bounds. Yeah, okay. And that should be it. Okay, now let's do get token integer. So what get token integer does is converts the token into an actual integer. We already put the character into RBX. We have, but it's also in AL, so we can just use the AL version. Yeah. So AL has a byte which has the highest. AL has the byte that has the highest significant decimal digit of this integer. So we need to first move it into BL. So we do move %AL BL. BL should already be 0. And at this point we need to keep on parsing till we see integers, right? So I think the right way to do this is LQ $10 with %RBX to EBX, and then we do add Q EBX. This probably needs to be AX. Are the higher bytes something else? Make sure that it's zeroed out. RX needs to be zeroed out. Okay, so yeah, so this should be fine. So RQ says %RX EBX. Yeah, so we have shifted the EBX by 10 and added it back. And now we need to check, we need the next character. So we do move be %r10 into al, and we need to check if it's the end of the integer. So we need to see if it's less than, if it's less than 48 or greater than, actually no, it has to end in a space, so you need to simply check if it's less than 48. Yeah, so you simply check if compare $48% al. This also needs to, okay, if it's less than 48, meaning it's a space, then we jump to read till end, or consume spaces, sorry. So this will need the next character, clean it out, test it, and yeah, it will finally move RAX into RBX though. Is that fine? No, this is not okay. No, we'll have to call it, not jump to it, because we need to make some changes. Yeah, conditional call. Okay, do it like call consume spaces. The way we're gonna do this is it's just gonna be jump on greater. Jump on greater than or equal to get token integer. So yeah, just loop back to get token integer, which will dump it into it, else it will just call consume spaces, and at this point all the spaces are consumed. EBX has our integer constant. We just need to move token integer into RAX and return. So what this will do is first shift and put the constant into EBX if it is, then read the next one. If it's an integer constant, put it. If it's anything less, yeah, it cannot be anything else, so it would be, yeah, then it would call consume spaces. Consume spaces would go and read all the spaces. Yeah, read the next one and move back, move RBX into RAX. This is fine, we don't really care about this, we're going to discard it anyway. And then we move our stuff into it. Okay, this sounds perfect. Now what we're going to do is write a loop that goes and from the program source, we're going to simply say token loop, right? And inside this, we're going to say call get token, and we will inspect it manually. to see if it's correct. Eventually this will go to program end loop. Sorry, what is it called? Program end, program parsing end. To define here. We should define it in the tokenizer. Oh, we already have it, sorry. Okay, and then jump to token loop. Okay, expected comma for token constant. No such instruction append token. Number of appends mismatched for null. Is it, should I use imul? Multiply or register by 10. Yeah, just be imul. Attempt to store non-zero value in section BSS 139. Buffer is already. Let's give it a name. Welcome symbol length. I guess I don't need a separate label for it then. Okay, attempt to 0 non 149. One more thing, token identifier cannot be used when making a buyout. I think I referred to it wrong. That seems correct. Oh wait, this token constant. There we go. Create. Something happened, might be in the loop. Let's go to this. So we're about to call token loop, get token, right? Let's do next. Let's check in. Oh, event to program parsing end directly. That seems wrong. I'm gonna have to debug this. Okay. So we're going to get token, all registers are zeroed, removing the first byte into it. 0x6, actually we can do C, right? I, okay, so the int, I'm guessing, was the file. Yeah, int main, okay. So I has been passed, do next I. So it's gonna compare which one it matches against. Moves it to BL first, compare AL is false, it shouldn't go. Oh. That was easy. Jump on 0. Oh yeah, I mean, if I do AL, it's always going to be 0. What was I thinking? Compare AL, just subtract AL from AL. It's obviously always going to be 0. Okay, we have a segmentation fault, which is better. Why did it go to token identifier? That seems wrong. Let's run again. Okay, so this time program passing in is not going to happen. Special character is not going to happen. Integer is not going to happen. Special character is not going to happen. Identifier should happen. Okay, so it did get into identifier. That's good. Why is it calling read till end? Yeah, we just want to consume everything that's there. That's not spaces. So step I, next I. 0, shift and continue. So now we need, let's see, p/c $al. It is n, which is correct. Next I, next get token in, no. Oh, we need to have a loop back somewhere. No, it's checking if it's a space, then it's space. That's not true. It shifts RBX by 8, moves AL into BL. Perfect. Let's try to print BX here. Oh. So it is x86c, which is correct. Okay, this is good. Now, next I. This is fine. It's fine. This is fine. This is fine. At this point, T must have been added, right? Okay, p/x $rbx. (69CE 6074). That is INT. Perfect. Next I. Now the token must be space. p/c person $al. 32. Perfect. Next I. This should compare true. It should consume spaces. Perfect. And then it's gonna read R10 AL. Increment R10. Is it 0? No. Is it a space? No. It goes to deq R10. Perfect. Move RBX to RAX. Return back. And the return goes to get token identifier. Perfect, this is good. So we have created the token successfully, and it is stored in RBX at this point. So we're going to dump all those registers into the identifier table. So this goes to next. P/x $RBX is 664. So this is correct. Higher bits at 0. So the next add. Oh, that itself failed. So what did we do wrong? Move RBX into RX. Oh, identifier table. No, it should be identifier table, not identifier table, it should be identifier table end. Bad. It was reading the first byte of this. Okay, this should fix it. There we go. Okay, so it is stopped at program parsing end. Perfect. We just need to debug every broken loop and run. This is the first one, so we continue, print P/x $RAX. It's 1, so it's at. Okay, so we also need to handle keywords now, right? So after the identifiers have been passed, we shouldn't just directly put them into the identifier table. So it's actually get token identifier and keyword. Get token identifier, yeah, and keyword. So we need to now know if it's a keyword or if it's an identifier. At this point, RBX, RCX, RDX have like the completely filled in value. We need to check if the first one, if it's a keyword, it would be one of the valid keywords. So what we need to do is we actually need to just create a table of valid keywords and then match it against that. So we just need to put like 8 bytes worth of like keywords everywhere. So we're going to do this at the beginning actually. Then do it in the text section, or data would be actually fine. Data keyword table, right? And then you're just going to fill a bunch of quads in it. The unfortunate part is we need to somehow convert them into like hexadecimal values. So I'm actually going to just write a Python program for it because it's just easier. Encode keyword py. They are stored left to right, so actually it's not that complicated. Yeah, we just need the hex representation of it. I think this is fine. It's just not too bad. We don't need a Python program for it, we just need a terminal. So if I say int dot split we need for each def encode quickly print. No, this is annoying. Should simply say ord hex of ord of x for x in 696C74. That's what we wanted. Okay, so now we go back to our keywords and copy them over supported keywords. They're not actually keywords, but you get it. Okay, so the first one is char. Six three six eight 6172. So this one's 6. Should I just generate this? I think I should generate this. It's not annoying. Encode keywords.py. If and now return size of and that should be it. And now we simply say for what is hex print? I think this should work. C is not defined. Not join. Oh god, I don't know enough Python for this stuff. I'll flatten this. Yeah, join is, oh, of course. All these 6 digits, 1 2 3 4 5 6, and just making sure they're even numbers and there's no, the zeros are handled incorrectly. That seems fine to me. So these are our keywords now. But actually, instead of putting these keywords here, what I'm going to do is I'm going to change this. I'm going to, instead of just doing quad, I'm going to say keyword underscore plus k. I'm going to do EQU on it. So I'm going to define constants right away. Keyword plus okay. And then I'm separately also going to print the quad keyword underscore k. So I can then put that into the table. Okay. There we go. So now we have our constants defined. and those constants will be put in the table. Oh, I didn't define it correctly. Need 0x for this. Now we have the keyword table, which is perfect. And now finally we need to terminate this with $0. So this, so if you want to check if a particular identifier, if a particular identifier is one of the keywords, the easiest way to check that is just a loop through this and check if it's one of them. However, we also need to make sure that RCX is 0, because it could be an identifier called continues, continue with an S. So we want to first make sure that it is the rest of the bytes are all 0, which is in RCX, sorry, not RBX. Okay, so now what you're going to do is get token identifier. We have read it. The values are filled in. We say compare test q RCX, comma %RCX. If it is jump on not 0 to store identifier, just defined here. If the higher byte is if the higher register is non-zero, it means there is more than 8 characters, so it has to be an identifier. There is no other way. If it is less than 8, then we'll check if it is one of the tables. So we say keyword table of into RBX now, because it should be empty. Now we're gonna say compare RBX, comma RAX. Jump on not no. Before we load, we first need to compare if it's 0. If it's load the value first. So if we have reached the end of the keyword table and we haven't found one of the matches, then it must be an identifier. We can jump to store identifier. Oh, but before we jump to store identifier, we have to make sure that since we have filled up RCX, RBX now, they shouldn't get dumped along with it. Yeah, that's annoying. We need to clear them up. Not a keyword. We'll first clear the higher registers. RCX, it should be RDX. RCX and RDX would be clear. and then we can go to store identifier. Yeah, this is correct. Okay, so if we have reset to the table, it's not one of them, it's done. Otherwise, we go to, when we compare rbx with rdx. If it's jump on non-zero, we go to the RCX need to be incremented. The annoying part is I need to increment and then loop back. Just implement it. Just increment it anyway, and then compare rdx. If it's not 0, then jump to next keyword. Check next. And if it is equal, we know it's a keyword, so we can simply return. Yeah. And if it's a keyword, it's already in rbx now, so we just need to move to rax. Which read till end anyway does. Yeah, moves rbx to rax anyway. Oh, read till end has it in rbx and rx. Yeah, rbx and rx. That's okay. We can just use rax here. That's fine. Can I use rax? So that way I don't have to do this not a keyword nonsense. Let me try. So suppose I move this into rax. I have to still move it somewhere because I need to compare it and I can't do two memory operations. However, I can actually do this without moving. I can do compare vertex 0. Instead of doing test, I can also do test. Yeah. If it's 0, then we can simply jump to store identifier. Yeah, this is better. We don't need this now. It has an rbx and rax. Great, this is good. So I'm going to reuse rax for that, and make sure already have what we need. Check next keyword. Well, instead of moving, okay, this is checking if it's 0, incrementing rcx. No, it will be rax now. Compare, yeah, this is different now. Instead of comparing rbx with this, we compare it with, okay, great. And if it is equal, then we just move that into rax and return. Perfect. I think this should handle it. Okay, 130, 136. And define reference to $0. Okay. Something is happening. We just need to check what the tokens are now. Okay, we do break token loop. First time is nothing. Continue p/x $r ax. It's 1 again. Why is it identifier again? This time it should have been recognized as integer. We have added integer there, right? Yeah, we do have integer here. Okay, we just need to step through and check what's wrong. Yeah, debugging assembly is fun, but you have to just step through everything. It's hard to put breakpoints on lines or anything like that. You can put breakpoints on addresses, but this is just easier. Okay, so this goes into token identifier and keyword. It's good. I'm just gonna do next I. Yeah, and at this point I can check if the registers are correct. So we have RAX has this. RBX should also have the same thing. Yes. RBX should be empty. Nope. Oh, sorry. RCX should be empty. It is empty. Great. So this will not fail. This will go ahead. Okay. So now we have loaded the address of the table. Test queue. Wait, test queue 0 doesn't do what I think it does. It's just going to AND 0 with RAX. It's obviously going to. No, this should be fine. Oh, I did jump to store identifier. I want to make sure that it's not 0. How do I check if something is 0? Yeah, this is on me. Here. Check if memory location is 0. Compare. The 0 flag is not set by test. Okay, this time it's correct. Now we have int as the token. This is great. Now we do I think this should still be correct. Okay, yeah, continue. Same one again. Oh, it's because it's get token. Token loop. We have identifier now. Perfect. Which is correct because our program is int main, and let's check what the identifier index is now. Is 7FFF. That seems wrong. The index should have been into the table. Okay, so we messed up somehow with store identifier. This looks like minus. Yeah, this is bad. Store identifier. So what this does is loads identifier table end into RAX. It shifts it by 32, then moves it back into moves the needs to store at the end of identifier table, not in the identifier table. And then LEAQ identifier table, the beginning of the identifier table into RBX. This is correct. Subtracts RAX minus RBX and is the order wrong? Destination equals to destination minus source. Oh. Yeah, so we subtract RBX from RAX, shift RAX by 5, move RAX back into RBX. This seems correct. Break token loop. We are already 3 hours into our stream and we have just finished tokenizer, but compilers, it's gonna be somewhat easier because we're gonna do compiling and tokenizing, sorry, parsing together, so hopefully this catches up. Integer identifier, it's 1, that's perfect. Identifier again, that seems wrong. It should be parentheses. Interesting. It's just printing identifier now. Yeah, this is wrong. Start from the beginning. So the first token was correct, second was also correct. Let's try the third one. Get token, okay. This should be open basis, right? It is open basis, okay. Not pressing in, it should be token special character, which it is. It's immediately gonna go to jump till end. Get shifted into RBX, so it's 28, which is correct. 40, yeah. Loads a new one, increase R10. Is it not 0? If it's a space, yeah, there should be a space. What is it, by the way? It's 20, yeah. It's supposed to consume spaces. Gets to token in. Wait, why is it 28? Yeah, the bracket's right. Goes into RAX. This is correct. 28. This is correct. Next. Last to token loop. Yeah, it's 50. Wait, why was it 1 last time? Did I make a mistake while debugging? First one is empty. 6964, continue. It's 1 identifier, correct? Continue. Hey, it was just correct. What was I thinking? I don't know why I thought it was wrong. 29 closing bracket, correct. Continue. Then we have curly braces, which is 7b, that's correct. What's the next character? We have return 0, so let's see. RETURN, that seems correct to me. And then it should be integer constant. Integer constant, perfect. And we'll check what the integer constant is. It's 210. That's wrong because we're returning 0. Okay, we have to debug this. Integer constant seems wrong. Okay, we'll check this out. And then we have semicolon, which should be 3b. Is that correct? It's 3b semicolon 59. Yeah, seems reasonable. 48 plus 11. Yeah, that's correct. 3b, continue, p slash x is 3b again. That's weird. And then it gets stuck. Why is the last one 3b again? Shouldn't it be curly brace close, which is 125? Semicolon not being handled correctly. Semicolon is here. Shouldn't be handled correctly. Slash n is 10, right? Yeah. Okay, we will get to that later. Okay, let's test out why the integer constants are wrong. Get token integer. ML 10 into EVX, add EX into EVX, that is correct. Move R10 into AL, inc R10, that is correct. Compare 48 with AL. 48 is start of 0. If it is greater than equal, oh, we have to make sure that it's not semicolon. Yeah, you have to check if it's, yeah, that's what happened. Okay, let's think about this. So we have to make sure it is an integer. Oh wait, or we should just make sure that our program has a space. No, it does have a space, so it should not be a semicolon then. Yeah, it will be a space. Okay, so greater than equals to 48 is JGE. No, but I think it is. What does the JGE mnemonic mean? Jump if greater or equal. Okay, this is correct. The signed integers is going to be positive. That's fine. correct. Compare 48 AL. It's basically jump, not negative, right? Yeah. Hey, we are writing a bare bones C compiler in x86 assembly for a very small subset of the language, which is shown on the website below. If you look at the website under my picture, it says my website / x86c. We are sort of like constructing a small C language equivalent and writing a compiler for it in assembly and trying to keep it as simple as possible. We are currently in the middle of the tokenizer. We are trying to convert the source program into small tokens so we can next write the parser for it. Yeah, welcome to the stream. Okay, we're currently debugging why the token, when it's an integer token being passed, it's wrong. So compare 48 with AL, something. Yeah, we'll just have to step through this, honestly. Break. Token integer run. Okay, so we're at the beginning of get token integer. Let's check what our first digit is. It is 48. 48 is what? 0? Yeah, that seems correct. 48 is 0. Okay, so then we do next I. We add it to EVX, it's correct. So EVX should be 0 now. Unless I forgot to clear EVX. Oh, yeah. Okay, so this was the mistake. Get token integer. The first time it gets called is here. At this point, wait, this is the only place, yeah, it's called. So then RBX should be 0, right? Oh, here it is. We have BL already loaded. Yeah, okay. Okay, so what happens is we already have it stored. We did this for convenience. Yeah, so we read the character, we already put it into the BL register. So we need to not do that for the integer case. Let's just do a special case for it. Let's do get integer start, which will clear it out first. Okay. Is get token integer, we'll do get integer start, and then we'll just clear out RBX. Okay, and this will fall through to get token integer, so that way we will add it back again. This shouldn't create a problem anymore. Token loop. First one continue. Okay, so int is correct. 1 is correct. That's identifier. 28 is parentheses, closing parentheses, curly braces. This should be return. It is a return. Continue. It is integer, and we should check the integer value. It is 30. Yes, because I forgot to subtract 0 out of it. Perfect. So the only thing that needs to be changed now is when you do get token integer, multiply, and you before you add, you do sub what is it, 48, right? ASCII, right? It is 48, yes. So we subtract 48 from AL, or we can do EAX, and that should be correct now. Okay. I wish I had a way to print out the tokens. That would be easy, but we have chosen not to do that. Okay. Break token loop. I have to define a macro for this. Typing this is getting annoying. Can I actually do two commands in the same line? GDB two commands in the same line. Is there an ampersand and thing? I can make it into a function. Oh, you can. Okay, perfect. So I can do continue p/$rx. Of course, Gemini is hallucinating. I'm gonna have to define it. Define C and P. I'm gonna say C p/$rax p/$rbx. Type everything. Okay. C and P. 69. This is int 1, correct? Opening parentheses, closing parentheses. 7b is curly braces, and we have return. Then we have 2 and 0, perfect. Then we have semicolon, and then we have closing curly braces. Wonderful. And the program ends. Okay, so mostly our tokenizer is working correctly. I'm going to commit all these changes. So git ignore, makefile, readme.md, source driver, source tokenizer. And then I should also probably add the scratch. I should, instead of calling it scratch, I should say examples. Examples empty. Gets finished basic tokenizer. Okay, so if you're following along, we now have that x86c. Oh, I mean, we should just check it from here. So on the website, we have a link. I should make this into a hyperlink. Okay, so we have the basic tokenizer filled in. Feel free to run this if you want to also try it out. Okay. Next stuff is to parse declarations, and the first thing to parse is variables. We have global variables that need to be parsed. There are 3 types of global variables we will support in the beginning. Since we're supporting types only char, int, long, and pointers, let's do pointers later. Let's start with char, int, and long. We have to basically, there are 2 types of top level declarations we can have. One is variable declarations and function declarations. And let's start by looking at how they would look like in each case. So regardless of whether it's a function declaration or a variable declaration, it will always start with a type. So we will have a type. Followed by an identifier. If this is the case, then it's a variable. If it's a type, so if the type identifier semicolon, we will not support initialization of variables for now. We can support it later, which we will actually, no, we might have to. Yeah. So if it's type identifier semicolon, then it's a variable. If it's a type identifier equals, then it's also a variable. If it's a type identifier open param, L param, then it is a function. Okay, so by the way, we also need to start defining more constants now. because it will be easy to refer to tokens by their name as opposed to having to write them. Actually, can I write inline? No, it's just easier if they're converted into tokens already. So let's say so in this tokenizer, we're going to now define more tokens. Yeah, so we have all the special characters will basically be tokens too. For keywords, we can directly just compare with the key. We already have the keyword constant, so we don't need to define tokens for them. Yeah, the keywords themselves are tokens too, so that's fine. We just need it for the special characters, and the special characters that we are supporting are here. Let's copy it from the website again. These are the special characters. I should just write a program again to generate tokens for this. This is just annoying. Okay. We say special chars equals. This is annoying. We will use some Vim tricks for this. Comma, replace with new line. Great. And oh, there's a space here. Never mind. Just remove it. And then this comma becomes comma. We still need names for them. It's gonna be annoying. Yeah, let's just do this by hand. That's fine. I should have also added parentheses. Oh, come on. Great, and now I give them names. So L param, R param, star, amp, claim, semicolon, comma. Is it comma or double L? Plus, minus. You seem seasoned with seasoned Vim Wizard. I am so, like, I mean, that's the only editor I use. Vim is all I use. So yeah, I've picked up some tricks along the way, but I'm actually very tired. I've had very less sleep, so I'm just like struggling a little bit with it. This should have been easier. Divide %, but yeah, Vim is all I know. I'm gonna call this assign not, and this one's to be equals, because the tokenizer already takes care of converting it into tokens. Let's say less than, greater than, less than, equals. This is too long. It's fine. Let's call it less equals. greater equals not equals L braces and R braces. All right, and that is the end of this. You just need parentheses and oh, what did I do? Just need open parentheses at the beginning. Okay, so now we're going to print the tokens for each one of them. For SC in special chars print, we need a keyword for it. So what's the equals token underscore plus SC of 0 plus. Okay, so now we need to convert these into the encoded version, which we have function for. Encoded equals to SC of 1 plus encoded. Okay, and now we do Python 3. Okay, so now we have our special character tokens. I did have it open. For indentation's sake. Okay, so now we have our tokens defined, we have our keywords defined, and we have our keyword table. We just need to start writing the parser. So I'm going to merge the tokenized. I do want to write it separately though. I don't want to write it in the same file, but then these EQU ones will have to be carried over. Let me check if GSM, no, it's not going to be handled by the linker. I'll have to copy it over. I think I should put it into an include file. Yeah. But it needs to not be in the source file. Yeah, this can be done. Source defs.inc, and so these all go into here. How do I include a file in GSM? Dot include, perfect. When invoking, you can do -I. Okay. So I'm going to say defs.inc. And then we'll change our make file to handle this correctly. Okay, so this goes here. Now we need a new source file, parser.s, which will also include our defs. Okay, great. And now we say we have inside the parser, we'll define a function called parse tu. So parse tu is parse translation unit. Which is going to handle the whole translation unit. But obviously what this is only going to do is just call parse TLD, which is top level declaration in a loop. So we will just do that. Call parse TLD. And the parse TLD will then decide which type of is it a function or an integer separately. So jump parse tu. the tokens, when the token ends, it'll stop anyway, so that's fine. We will later add a special token for token end, which will be returned, and then TLD can check for that, or parse_tu can check for that, so we don't have to worry about that, right? Okay. Now let's define parse TLD. Okay, so when parsing, the first thing we'll do is just get a token. So we'll say call get token, right? Now in RAX we have the token. Of course, the first token must be a type because that's the only valid syntax. We are not going to do, we should probably write this down. Tokens should be separated by space or tabs or new lines. And we should also say that minimal parsing errors. We will report some errors, but yeah, we will do that. We will like do that here, but okay. So then actually, you know what? Let's handle it a little bit. Let's call parse type because it has to be a type, right? And if it's not, we can error out. Okay, so we will define parse type. Now, parse type will do the get token. And the job of parse type is to then also return the type to the caller if they need it. So we'll say get token, and at this point, all we have to do is like check which token it is. Like it has to be one of. Keep it open. Source def. So it has to be either keyword char or keyword long or keyword void. Like it has to be one of them. Char, int, long, or void. So we will just check that. I mean, one way to do this is to make a table of valid types and iterate through them. But since it's just 4 and maybe one pointer type, we will skip over that. We'll just write 4 comparisons. So we'll say call get token, and RAX must have the right token. So we say compare q dollar keyword underscore char comma RAX. Jump on equal parse type done, which we'll define later. Compare, and then we can just copy this over a bunch of times. So we can say yeah, it's not the nicest way to do this, but since we only have 4 types, we can cut those corners. What was it? Char in type long white. Okay. And if it's neither of them, then it's an error. So then say jump to, actually just report there. Yeah, jump. We need to load the error strings first. So if we go to source driver, we can copy over. Yeah, we'll just copy over these error messages. So we have this is file not found. Need to get some name. We'll say PE equals parse error expected type. Parser expected type equal PE expected type len expected type. Yeah, so we now have our error messages. We just load them. So we say move q% q PE expected type of RIP into RSI. RSI or RDI? Sorry. RDI. Move Q dollar PE expected type len into RSI. This is the length of the error message, and then we simply jump to report error. Okay, so what this is checking is it has to be one of the types, and if it's not, we report an error. And then if it is an error, if it's one of the types, we say just return it. So the type will be returned in RAX, which is the keyword itself. And that's good because we can then do things with this type, like put it in a symbol table alongside the name of the variable or the function and so on. So let's go back to our parse TLD function. So by default, every TLD must start with a type. That goes without saying. Now we have to pass an identifier. So we do get token. We call get token. So this would, we can store this type somewhere in a local scratch. Actually, this is the point where we can start using our global registers. Honestly, for this one, we can move it to tokenizer uses RBX, RCX, RDX, RSI. We can keep it in RDI, the type if we need it. Yeah, we do need a type because we need to figure out how much memory need to be allocated for this. Okay, so we have the type in RDI, which is going to be untouched unless some error messages or something gets called, which is fine. Okay, and then we call get token. So now we have, this has to be an identifier. So we say compare keyword, no, not keyword, sorry, token identifier, comma, RAX. If not, we should prepare the registers. No, we can't prepare registers because RDI is currently holding the type. Yeah, this is the annoying part about using RDI because it's interleaved use for something else. So let's use R11. We should write it down somewhere. So we'll write it here. %R11 type of current TLD. Okay, so R11 contains our type now. Now we call get token, token identifier, and at this point we can prepare the error message if it needs to be called. So we can say AQ PE expected identifier. I mean, ideally we should do this move inside the jump, but this helps, like, allows us to not have to create unnecessary labels here and there. We can just, it's slow, but it's fine. It's not that bad. Just 2 extra moves. It does pollute registers though, which is annoying. The places where we do need to keep those registers occupied, we have a conditional jump there. Okay, so this goes here. Feel free to ask questions, by the way, if something is not making sense. All right, so now we have the TLD has parsed the character, the type, the name of the function slash whatever, Um, and it has also, it hasn't yet decided whether it's a function or a uh, or a variable. So we will check that. I'm a data engineer, by the way, so anything here doesn't make much sense to me, but I'm still learning. Oh yeah, I mean, I'm happy to like get into details of stuff. I think the whole point of this is to understand how compilers are written without like an existing compiler from very low level stuff. And the big picture stuff that I'm doing here is I'm cutting corners. So instead of implementing the full C standard, I'm restricting it to something that's easy to parse, easy to compile for, do minimal type checking, do no optimizations essentially, but still have a functioning compiler that can execute C code. And then we can use that to then build a fully functional compiler, which can then do more things for us. Yeah, and the follow-up stuff we'll do in the next session. So any pre-reading material to go through, should I just chat GPT it? You could chat GPT it. It's not really pre-reading material. I mean, general C compiler slash like compiler pre-reading material is good, but this is also a good blog post it's a very old blog post. It doesn't really have the same motivation as what you're trying to do, but it also did implement a C compiler in assembly in a very small, like 512 bytes only. There's like some tricks here. So it's not really pre-reading material because you need to have context about what each of these things are. I would say general compiler, like what are parts of a compiler, what's a tokenizer, what's a parser, would be a reasonable like pre-reading material to have. But yeah, I mean, since you're here right now, if you have any questions, just stop and ask me. I'm happy to answer. Yeah. Okay, so we have, I'm just gonna, yeah. So we have picked up the type, we have picked up the name of the variable. We should now check what, if it's a parentheses or if it's an equals or if it's a semicolon. The three possibilities at this point. If it's opening L param, then it is a function call. So we say cmpq token underscore L param rex. So if it's a thingy, then we jump to if it is at L param, then go to parse function. Right, now we're going to parse function. I think since it's a parser based thing, we can just simply assume if it's not an L param, then it is a variable. But we still have to check whether it's an equals or semicolon. So, but I'm gonna in all the other cases, I'm gonna say jump to parse global variable, right? There's two possibilities only. And yeah, this is not reachable. So let's start with parse variable, maybe, yeah, parse global variable, since this is easy to write. So for variables, what we're simply going to do is we're going to record the variable in a symbol table. So we say this variable is live, and other than that, we are simply going to what should I say? And after that, we're simply going to allocate space for it in the code generation area. So we'll have an executable area /data area where we'll just say, okay, this variable is of type integer or char or whatever, leave that much space for it, and remember what the address of that was in the symbol table. So whenever that variable is referenced, we can then just shove that address into it, and that's easy. Which actually reminds me, our identifier table, we made a mistake. Before throwing stuff into the identifier table, we need to make sure that it already doesn't exist in the identifier table. If it already exists in the identifier table, we should give it a reference to that. Yeah, okay, I'm gonna take a quick break, just like a washroom break, and I will be back in like 5 minutes, and then we can fix this to identify. I've been drinking a lot of tea, so I need a few seconds. I'll be back. So what I was saying is when we look at identifiers, we should deduplicate them. Instead of adding them into the identifier table immediately, we should check if it already exists in the identifier table. And the benefit of that is next time when we are like when you're looking at two variables, and if you want to say if they are the same variable, we can just compare their index in the identifier table. We don't have to actually do string comparisons on them. So the only small change we need to do is we need to first check if the identifier already exists. So this is store identifier already has there are just the whole identifier in RBX, RCX, RDX, RA, RSI. We need to first go and compare. So let's do the loop. So we're going to say move Q. Yeah, I guess we have the, no, that's the end. We need to do move Q identifier table of RIP LEAQ into RAX. So we have the start of the table loaded. Now we're going to do comparison of RBX with RAX. Like we'll make sure that it is the same. If it is not equal, no, if it is not equal, then we go to next identifier. So we need to add to it too. So we can say LEAQ 8 of %RAX, %RAX. But this shouldn't happen the first time. Just need to go back a little bit, right? Yeah, so how do we do this? We could also just leave the first table table entry empty. And just do sub q, it's fine. We can do LEAQ -8 RAX. Okay, so just like offsetting for the first one, and then we shift it by 1, compare if RBX matches RCX. If it is not equal, we go to check next identifier. But check next identifier should also make sure that we haven't gone past, right? Yeah. Check the identifier to check compare Q %RAX. Should add 1 and then check RAX with, what is it, identifier table end of RIP, right? So yeah, identifier table level of RIP. If it's equal, then we are store add new identifier, which is here. And we don't need to do this again because we literally just have that. Yeah, okay. Okay, if we have ran out of all identifiers to compare, we go to N. If it's not matching with this, go to the next one. Then we compare %RCX with %RAX, no, RAX of 8. And if not, do this. Just copy this a bunch of times. RDX of 16 and 24 with RSI. Okay, so this will check all of them, and if they all match, which means there's an exact one, we just need to return that particular index. So at this point, we can do this math again. Yeah, so we don't need to do any more stores. We can just do this subtraction thingy and move it back. So we move the identifier table start into RBX. We subtract RBX from RAX. Oh wait, can we use RAX? Right, this cannot be done. So no, this is fine. Yeah, RX minus RBX. We shift 5 by RX. The index is moved. Yeah, this is fine. This is fine. We don't need the identifier anymore. Yeah. So this honestly is exactly the same as this one, right? Yeah. So we can simply say add new store identifier finalize. We just jump there. This is exactly the same, so why bother? Store identifier finalize. Okay, so if it matches, then just go there. Otherwise, you go to add new identifier, which we don't. Am I even referencing add new identifier anywhere? I am. Okay. Oh, if we have a note of everything, we need to go there. Yeah, that's right. And that's good. So this will add the new one. Finalize will just yeah, this seems correct. We are only using RAX, we're not touching any of the other registers, so this gets stored. We finally have RBX with RAX, shift RAX by 5. We do have RAX moved into RBX, that will give us that. This is perfect. So this will deduplicate tokens, so we don't have to worry about it anymore. Okay. Now, let's go back to our parser. Okay, so we did parse global variable, right? Okay. So parse global variable, we already have the variable name. We just need to check whether there's an assignment to it and whether it's also semicolon. So I'm first going to handle the case where it only has a semicolon, which means the variable is uninitialized. So we're going to say get token. The name is still in RAX RBX, right? Right, so we need to move that somewhere. Move q %RBX into R12, and that adds another global, which is name of current TLD. Name of current TLD. TLD is top level declaration. Okay, so we've moved RBX into R12, so we don't forget that. We could honestly just do that here. Yeah, because it's common for both of them. Oh, no, not here, sorry. Here. Okay. So that's the identifier. Let's do it maybe here. Yeah. Okay, so we get the L param. Yeah, I wonder why I didn't store the name. Okay, so now we need to check whether it's semicolon or equals. We need to get that anyway, so we say call get token, and now we say compare token underscore semicolon RAX. If it is a semicolon, then we simply say jump on equals parse global end, which is just here. So we say parse global end. Otherwise, so for now, I'm going to say variable initialization not supported. I'm going to print out an error message yet. No initialize variable initialization not supported. Var no init. Okay, var no init len. var no init of RIP into RDI. Move QPE var no init len into RSI. It can be ESI too, but that's fine. And then jump Q report error. Okay, good. Okay, parse global end. What does this do? This is just saying the variable is done. So for now, what we're going to do is we're just going to return, right? We will add the code for this later. I just want to make sure that this works correctly. So we have parse TLD calling parse TU again, but instead of parse TU, I'm just going to call parse TU end. And just to debug this, we're going to just parse one for now. Eventually, we will change this. And then now the driver, instead of calling token loop, just calls parse TU. This should work correctly. Where is the parse function? Yeah. Just define parse function somewhere. Just return. Okay. Unsupported syntax for jump 48. Okay, invalid operands for this. What's the line number? P expected identifier len. Invalid operands dot text and undefined section for minus when setting P expected. Wait, did I change? Why does this not work? Expected identifier len, comma, expected identifier. Oh, typo. Should be identifier. Okay, let's see. Warning relocation against expected identifier need only section text. This is in. Okay, there's a bunch of undefined message first. Identifier. Why can't I type identifier? Okay. Undefined reference to report error. Yeah, so report error is not defined as global, which we can do here. You can say global report error. Okay, one final in function store identifier finalize. There you go. Okay, since our current function just contains a main function, this will jump to parse function and should get stuck there. Let's try it out. Okay, it does get stuck. Let's make sure it gets stuck in the right place. Let's put a break on parse function. It does reach parse function, so that's good. Let's make sure that the variable name is correct. It should be in R12, right? Actually, first let's check if the type is correct. So type is 6909556. which I think is void. 6909. No, that's, first of all, it's odd numbers. 69. Oh wait, that's decimal. It's like, oh, it's okay. 696E74. This is int, right? It is int. Okay, perfect. So the return type of this is correct. We want to make sure that the name is correct too. Index 1. And we can also check what that is. So we can do p of identifier table plus 1. Oh, needs to be char star. Okay. Oh, no identifier table. We need identifier table address of identifier table. Yeah, okay. There we go. So it is IAM. Where's the N? Oh, this plus 1. Here, so it's main. That's correct. So, but why is the index 1 then? Did I do the math wrong? Yes. When returning indices, we should subtract. Yeah, so store identifier finalize should give us the CQ. Yeah. We'll just make sure that it's correctly subtracted. Okay, this looks correct. So main was parsed. Now what I'm going to do is I'm going to change the example a little bit and add a variable declaration at the top. So I'm going to say int foo. This is a variable, right? Okay, that's bad. Okay, parse TLD. Start from parse TLD. Out ASM, which should be parse type. Then we check for identifier, should go through. Okay, then we check for this is checking if it's lparam. It should not, so it should go to parse global variable. Perfect. Should call token again and check if it is semicolon, right? Yeah, if it is semicolon, it goes to parse global end. Huh. That seems wrong. Okay, this is also a problem. First of all, we'll fix this. The segmentation fault is coming because of this being wrong. Okay, it says variable initialization not supported. That's wrong because we are not trying to initialize the variable. Okay. Token semicolon RAX. Did I? Of course, I forgot to put space. Variable initialization not supported. This is wrong. Okay, time to step through this again. Parse global variable. So at this point we have already parsed. Oh, we have already parsed it. So we directly compare. We don't parse. We don't call get token again. Yeah, we've already parsed the L param or the token to check whether it was on left parentheses or what. So we just simply check if it's a semicolon or whether it's an equals. Okay, this should work. Nope. Okay, this does work. Okay, so now we have finished parsing a variable. Um, Now we do actual code generation and symbol table creation. So one big difference what I'm doing is I'm not implementing an IR. I did think about this a lot. Do I want to actually implement a small intermediate IR and then do some transformations on it before code generation? But to keep this simple and tractable, I'm actually just going to skip over the whole IR phase and just code generate from the parser. As you parse it, you just start emitting instructions for those functions and for those variables. So it's a easy way of implementing a compiler. So okay, let's uh, we need to like write the binaries to the file and do all that stuff, but I'm not going to do that. I'm actually going to take a small trick here where instead of generating code to like a file, I'm just going to generate the code in memory. So including data, including variables, including code and everything, and then just simply jump to that. Just simply call that code. And that way we don't have to like, yeah, kind of an interpreted line. Exactly. It's not interpreted really, it's like JIT in some way because yeah, I'm parsing the source code in memory, constructing the instructions, and then just jumping to it. So yeah, it's like a interpreted slash JIT, depends on how you, I mean, it's not really interpreted because we are first going through all the code. So we are going through the whole C file, constructing the program for it, and then jumping to it. An interpreted language would sort of like go back and forth. Like once I'm done with the compiler, I'm done with the compiler. Never entering the compiler again. It's going to be all code. The reason I'm doing it in a separated way is I do eventually want to write the code to write the binary to a file so we can externally invoke it. So we don't have to like compile every single time. But for now, to test everything, I'm just going to like write it to a bunch of bytes in memory and then just jump to that. Which means we need to allocate memory for doing it. And one way to do that is to the mmap system call. But there's another way to do it, which is just to have a piece of executable, writable, readable memory in the executable, in like the same way we have in creating symbol table and so on, and just start appending data to it. And that's basically what we're going to do. So let's go and create a new file which will have the executable memory. So we say execution area.s. And for this one, what I want to simply do is I want to create a huge chunk of memory that's writable. So I need to have my own section. I just need to ask Gemini how to do this. In GSM, how do I create a section that is readable, writable, and executable? And the reason for this is I want to put everything into the same chunk of memory. I don't want to separate it out into like data section and executable section. It's just easy. So we do section and then thing and then proc bits. Proc bits basically says that this contains data that needs to be loaded. I actually don't want proc bits. Yeah, I don't want proc bits. I just want an uninitialized amount of memory. Yeah, so you can just do dot space. Yeah, that's what I'm going to do here. Dot section exec area. Oh no, it has to be dot exec area. AWX. AWX is A for? Sorry. A is allocatable, writable, and executable. What does allocatable mean? Allocatable, I think, simply means that it needs to exist. Yeah, it takes some space in memory. That's right. Read and write and execute, that's fine. And then we're saying at no bits. At no bits just says, I'm not providing what the bits here are, just reserve some space. We don't need any alignment for this. We just say code gen area or code gen buffer. This needs to be global. And this needs to be given dot space, and I'm going to allocate a bunch of memory. So I'm going to say 409,600 bytes. This is not part of the binary, but yeah, this will have some space allocated. And now what I'm simply going to do is, in the driver, before I call parse tu, I'm going to load the address of this in one of the registers. Program, what's it called? Code gen buffer. And the register we're going to use for this is you can use R13. Let's use R14. Code gen area, right? Okay, so code gen buffer RIP code. So yeah, we have a pointer which is pointing to where I'm currently spitting out instructions. Okay, execution area, this is fine. Okay, so parse global end, this is where now we will increment the pointer and then store the address into a symbol table, which means we also need a symbol table. Symbol table can be part of the parser. It doesn't need to be part of the tokenizer, but I'm going to copy over code. We actually need two different symbol tables. We need a symbol table, a global symbol table and a local symbol table, because we might have variables defined inside the function, and they need to be kept separately because they need to be cleared after every function, whereas global table stays forever. So we say global symbol table. And this is global symbol table end. I'm considering putting global, I think global tables can be put into memory. The address of the global symbol table, don't need a register for that. Yeah, okay. So we have a global symbol table now which has, and the way we are going to do this is 16 byte per variable, where this is identifier index, comma, code gen address. So for each variable, we're going to store what is the variable name and where it has been generated. And that's all we need to know. And yeah, and then later on when we refer to the variable, we just walk through the global symbol table and find the address of it, and boom, we have the name of the variable. We have the address of the variable. Okay, so let's do parse global end. So first we need to give this an address, right? So we need to know we need to allocate some memory for this variable. So the way we do that is by what is it, R14, right? Yeah, whatever R14 is currently pointing to is the address of this variable, and we need to register this into the global table first. So we go here and we take the last address of the global variable. So move q global symbol table end of RIP into, we can take it into RX, right? Yeah, take it into RX. And then we need to store the identifier first. So we move q percent R12, was it? Name of current TLD, yeah. Into RAX. So we're storing it into like the symbol table. Then we also store the address of this, which is the current code gen address, which is R14 into 8 of RAX, right? And we also need to then increment the array, the symbol table. So we say LEAQ 16 of percent RAX, and then move it, store it in the global symbol table. Done. So we recorded in the symbol table, and now we need to actually push the code gen value ahead. but that depends on the type of the variable. If it's a char, we push ahead by 1. If it's a integer, we push ahead by 4. If it's a long, we push ahead by 8, and pointer by 8. But to simplify everything, we can always allocate 8 bytes of memory regardless of what the variable type is. So we're simply going to do leaq 8 r14, r14, right? Done. So we don't have to worry about what variable type it is. We should, however, record the variable type somewhere else if we later want to do type checking, because when we have pointer dereferences, we will have to figure out what type of value it returns. I'm not getting into that right now. We can expand this later. Actually, we haven't even parsed the pointer types correctly. If it's not a pointer type, we don't really care. Maybe in the symbol table, we can record the size of this variable, so that way we can emit the right instruction for loading values from it. Yeah, that seems reasonable. Let's do that. So this is gonna be 24 bytes per identifier, and the last is gonna be size of variable. Unfortunately, we don't have the sizes in the register. We'll have to do some comparisons because what we essentially have is the token for the type, right? We either have keyword char, or we have keyword int, or keyword long, or keyword void. We should also, by the way, check if it's not void, because variable shouldn't be void, but that's fine. No type checking. Okay, let's actually just put an if condition and then yeah, store the type variable correctly. So before we do that, let's obtain the type, right? We'll obtain the type in rbx, and that should be okay. Yeah, so cmpq r11, right? R11 contains type of current TLD with keyword underscore char. Yes, this is just annoying having to jump everywhere. PGE char keyword underscore int %11 jpge int. I mean, if it's not int or long, it's gonna be 8, so that's fine. So if it's this in, I should just jump. That's right, PGE char move $1 into 16 PGE this is annoying. For 16 ix. This is PG done anyway, so this can be skipped, and here we do move cube $8 16% RAX. Okay, so what this will do is, depending on the type, it will store the right value, and then here it becomes 24 because it's 24 values per this thing now. Okay, and now this, oh my god, I keep forgetting. How much we increment by also depends on the register value. Let's go to register. I hate this. Writing a programming language in assembly. Yep, you're adding a C compiler in assembly. As annoying as it is. I'm going to simplify this. And in AT&T assembly, yep, that's the dialect of choice here. This needs to go here. I'm going to store the identifiers first, then compute the type, and the increment is this can be done afterwards. This allocation needs to happen differently. Yeah, so we're gonna move by one. No, we decided that we can move by 8 bytes regardless of what the type is. Thank God. Okay, so we first load the address of this global symbol table into array_x, and we store the name of the variable, we store the address of the variable, we check what type it is, if it's a char, int, or if it's a long or a pointer. Depending on those, we store the type into the symbol, the length of the variable into the symbol table, and then we finally and then we finally let me think about this. I think it might be easier to just store the type and then call getLen later on that type. I think this needs to be revamped. Sorry, give me a second. I'm really struggling with this a little bit. I'm just going to directly dump the type into the table. So R11 into 16% RAX. Yeah, we're not going to store the size, we're going to store the type itself. And the reason for this is we can compute the type later. We're going to add a helper function for that. But having a type will let us also make other decisions later. Like if we want to generate different instructions based on whether it's a pointer or whether it's an integer, a long, it'll be easier to do that. In fact, we need, if you want to support pointers to pointers, then we need to be able to store that too. So it's just easier if we do this. Yeah. Okay, so parse global variable has been done. This looks good to me, and this has been incremented, and we are done. Okay, and then parse. This can just go back. Okay, this variable has been parsed. It has been recorded into the symbol table, and we are good to go. Okay, let's check if everything works. At least compiles. Execution area also compiles. So let's try doing example empty.c. Well, it ran. Let's make sure that it works correctly. So break parse global variable. Actually, no, let's just go back to parse tu end. Okay, so at parse tu end, let's look at our global symbol table. It is 0, so there's a we should probably just do p/x. So 0, 8. 8 is what? The address. And then 2 is what? Oh, this is just printing the address literally. Sorry. To dereference it. Why is global table 0? Should be address of global symbol. Okay, yeah, so we have perfect. We have identifier 0, which is the name of the variable foo. Then we have 555, which is the address of that variable. Perfect. And then we have int, the type of the variable. Great. So we have yeah, we have int foo declared, code generated for it. End of story. We should test it a little bit more. We should also check long bar semicolon char bars semicolon, just to make sure everything runs correctly. And we should probably change this to jump parse to. Break parse to. Okay, this is the first one. Continue. Where's the command that we ran? Oh. P long star ampersand global symbol table +1 and just p slash. Okay, yeah, so the first one is 0. Its type is address is 900. Its type is int. The second entry's type is, sorry, the identifier is also 0. That's wrong. Its address is also 0. Oh wait, oh no, sorry, we haven't filled in there. Okay, so now we go to the second one. Identifier is somehow 3, which is wrong. It's not filling things up into the global symbol table. Let's check from the beginning. 0. Oh, it's overwriting the values. I think I forgot to push the global symbol table ahead. Yep, that's what I made a mistake at. So parse global. I'm writing it back. Oh, I did not increment. 24 of %rax, %rax. Yep, that should do it. Break parse tu, run, continue. I should write that command down. P slash x star long star and global symbol table +0. 0, 1, 2, this is correct. Continue. 0 is still correct. 3 is 1, 4 is shifted by 8, 5 is LONG, this is correct. Continue. Oh, parser expected type. Okay, we made some mistake. Parser expected type. What was the last one? Char. Oh, compare QRX. Yeah, this should have worked. If 2 ran correctly, why did the third one not work correctly? I have compare keyword char. Yeah, we will put a breakpoint on this and check it. Break parse type. Okay, the first time parse type comes in. ASM. Next. What? Oh, I did next, sorry. Next I. Okay. p/x $ix. It is int. Continue. Next I p/x $ix. This is long, right? Yeah. Okay. Continue. Next I p/x $ix. Huh. It's identifier. It's calling parse type somewhere where it expects an identifier. It got an identifier. Oh, maybe char is not being treated as a keyword properly. So we have keyword char here, and we have there's the keyword table. Maybe because it's not because the first one I maybe have an off by one error. Okay. Oh yeah, here I'm already incrementing it by one. One way to handle this is just to put an empty quad 0 at the beginning. This will take care of it. Still did not work. Oh, the very first is wrong this time. Oh, because it right away failed. I can put 1 there, I have to put 0 there. Sorry, I can't put 0 there, I have to put something else. I just put keyword char twice. Yeah, just handle it correctly, it's fine. This loads it, check next keyword, we can do aq -8 of rx. This will make sure that we don't skip over the first one. Yeah, this is better. Oh man, come on. Okay, int is working correctly. Long is working correctly. CHAR, is that right? 63686172. Six three six eight six one seven two. Perfect. So this can work correctly. Next I. That is correct. Parse type done. Next. Why does it compare? Okay, so this worked correctly. It goes back to parse tu again, goes to parse tld. Oh, this one it fails. Okay. This is void. No, this is int again. Okay, this is int works fine. And it should enter parse function now because the next one is a function. Yes, it does. And then it calls ret from there, goes to parse tu, jumps to parse tld. Right. Right, so once it's done with everything, it should stop. It should get stuck into parsing. The parser should get stuck, right? Not. Why does it say parser expected type? Should reach the end of the function. Should be 0. I'm gonna check what it is, the expected type here. I need to put a breakpoint on this. Fine. As expected type pre-jump. Okay, what is this then? Compare RAX. 29, what is 29? Oh, right, because we didn't handle the function correctly, it just tried to go back to TLD, right. So nothing is wrong, it's just we haven't done the implementation yet. 29 is space. No, wait, what? No, 0x29 is what? 41, which is, yeah, closing parentheses. Okay, so nothing is wrong. We just need to let's just implement parse function then and remove this. Okay, so now for parse function, I will first write a version that doesn't have. Actually, I should just support variables to arguments to the function. So let's just start with that. We're at 2:41 p.m. Eastern time. We have about 3 hours more of implementation. That's fine. We can get through basic variable loading and returning values maybe. Yeah, let's do that. Let's get up to at least loading variables, being able to return them through return statements, and then hopefully some basic arithmetic too. Okay, so parse function. We have already parsed the L param, which means now we need to start processing the inside of the parameters. Now it's either going to be a variable declaration or it's going to be a close parentheses, right? So let's get the token and figure out what it is. So call get token. Let's write the case where it is the closing parentheses. So we say compare %RAX with $R param token. Oh, I keep forgetting the order. Okay, and if it is a closing R param, which is jump on equal, we go to parse function body. Write this part later. Parse function body. Okay, if it is not a thing, then it has to be a type, right? Unfortunately, we have no way to put a token back, which is something that parsers have to do. So we have to do this. Yeah, so we can do parse type without actually calling token. So we do parse type no read. Just make a in the between jump. So this must be a variable. So if it's a type, it must, yeah, if it's not a R param, it must be a variable. So we say parse argument. So we go to call parse argument. Just goes here, parse argument. Now the type must have already been parsed. That's how we know that it is an argument. So we do call parse type no read. What it'll simply do is the token that has already been parsed, it's going to check what type it is, and it will do its usual thing and tell us that, hey, this is a type, for a little bit type checking. And now we get the name of the variable. This is similar to parsing a global, except that it's not really parsing a global, because we don't have to enter it into the global symbol table, we have to enter into the local symbol table. So let's do that. Okay, so we say call, no, not call, yeah, call get token. So here's an issue now. Since we are within the call argument, our type and everything will be overwritten, because our global variables need to be used separately. So before we jump to call parse argument, we have to save the type of the function and the type of the name of the function on the stack. So before we call parse, we say push q r11, push q r12. So this is the current function name, right, and function type. Yeah, we are pushing it onto the stack. So that way call parse can reuse those variables, and it doesn't have to. So this type is 11, right? Type is 11. So move q %rax into %r11, and now we get the name of the variable. Did we ever? So what did we do for global variables? Did we check if it is an identifier ever? We just assumed. Yeah, expected identifier. Okay, so we should just do this. Call token compare move. Okay. Okay, call token. Compare if it's an identifier or not. If it's not an identifier, then shove the error message. Otherwise, move it to RBX and RBX into R12, which means now we have the name and the type of the variable done. Now, so moving variables into arguments don't actually allocate memory in the global into the code gen area. It just allocates a stack slot. So we need to have a mapping between local variable names and the stack slot offset, which is easy. But before we pass the argument, we need to create an entry for this function in the global symbol table. We need to say that, hey, this function exists. We might have to do some bookkeeping for this function too, which would be on the lines of how many arguments it has and how many local stack slot it needs and so on. Actually, we don't need to know for all the functions how many slots there are. We just need to know for the current functions how many stack slots there are. So we can reserve either a variable or just a global like value. Yeah, that's probably easy. Okay, so we need to create a global variable in the data section, which is current variable stack slots. current function stack slot. So this goes to data, current function slots, and it just has a quad 0 inside, which we will initialize to 0 anyway. So before you start parsing a function, we say move q $0 into current function slots of RIP. Okay, so we zero the number of slots this function is taking up. Okay, we also need to create space for this local symbol table. Okay, local symbol table has 24 bytes per identifier. Again, we have the identifier index, we have the stack slot offset, and we have type of variable. Yes, and this is just local symbol table. Okay, and then we have the end of the local symbol table stored. So now that we have the type of the variable, the name of the variable, we just need to assign it a stack slot. So the good thing is function argument are already, like, they will still have a stack slot regardless of how many arguments there are. We will have stack slots for all of them, so that way we don't have to like remember which registers they are in, or we can free up registers for other things and we don't have to worry about calling conventions and stuff like that. Okay, so we will still enforce a calling convention for the generated code, which will look very similar to what we have. Like, we will use RDI for first argument, RSI for second argument, and so on and so forth. But we will make sure that they are still stored to the stack immediately. So the very first thing that each function will do is dump its arguments to the stack slots. Okay, so move q current function slots into RAX. Should be fine. Now we have assigned this as stack slot. We increment this q 8% RAX, percent RAX, no, not 8. Yeah, 8 is fine. Let's not do too much math. And then move q current function slots of RIP. So we have assigned a stack slot for this variable. Now we need to enter this into the local symbol table. So let's look at how we did it for the global symbol table and just copy the code from there. Okay, so this becomes local symbol table n of RIP. By the way, this needs to be reset to 0 before we do anything. So move q dollar local, should be leaq local symbol table of percent RIP into RAX into local symbol table n. So this will just like reset the local symbol table n. So we are just basically erasing all local symbols we have from the previous function if there was any. Okay, so now we do local symbol table n RIP into RAX. We store the name of this variable. We store the, what is 14? Oh, no, so in this case it won't be 14, it will be the stack slot that we identified. So this needs to go into RBX. We do this into RAX and then we copy it into RBX. It's probably easier. There is an easier way to do this. Okay, and then now RBX has the slack slot. 24 RAX into this, and then let's put this back into local symbol table n, and this doesn't need to happen. Okay, perfect. So we have now obtained a stack slot for this variable. The identifier has been added. Everything is good. And then we need to just consume the comma. So get token. There's two possibilities. Either we see a closing param or we see a comma, right? Okay, so compare q RAX token r param. Wait, why did I call it param and not param? Okay, token r parent, jump on equal parse function body. If it's not an r parent, it must be a comma. Which means we can go back to parse argument. But before we pass the argument, we need to get token again. And then we go to yes, we need to read the type. It's not a comma, then we need to read the type because parse argument assumes that the token has already been read. So then we call, no, not call, jump argument. Perfect. Okay, so the next argument is read. Finally, all these get finished and we reach call parse function body. At this point, we first consume the curly brace, right? I wish there was an easy way to do this. Yeah, call get token. Okay, so we consume the curly brace, and now we have a body of our loop. So we just jump to, should I jump or should I call? No, I should call parse statement. And parse statement will leave the last token. So we need to figure out when to stop reading the parse statement, right? Each statement ends with a semicolon. So after the statement is done, we check, we need the next token. No, but if we need the next token, we won't. Yeah, we have to read the next token to know if there are any more statements. So we call get token. We compare it to R brace, right? Compare token R brace. It's called R brace, right? R braces. Sure. R braces. Jump on not equal parse function body next. So token R braces. Next. But this means that the first token of the next statement has already been parsed, which means we need to also ensure this is done here. But not equal parse function body next. And if this is, it is a curly brace, then we do simply ret q. You might have to do some finalizing, so we can add here finalize the function. This might require setting up, cleaning up the stack frame, blah blah blah, as whatever code needs to be generated for each function. But before I do that, let me quickly, each statement must end in a return 0. Sorry, it must end in a semicolon. Yeah, okay. Yeah, we have to be able to handle returns in the middle of the function somehow. We'll take care of that. We also probably need a separate stack slot for return values. No, returns are happening in Rx. That's okay. Yeah, okay. So parse function body next. Finalize the function return q. Wait, did we add the function to the global symbol table? No, we did not. That needs to be done too. Let's just do that here. Oh wait, this should not go to jump to call argument should not go to parse function body. It should return from the argument. Sorry. Yeah, we can't have weird levels of nesting. This was called, right? Maybe I don't need to call parse argument then. Just jump to parse arguments, fall through to parse argument, right? Yeah, there's no recursion, we don't need to have scopes here, because you can't have functions and like arguments inside arguments. We can just linearly walk through the, yeah, I think this is fine. Which is also what is happening here. These are exactly the same. So you should maybe simplify this a little bit. You should do the resetting part here as part of call function, and this can probably be simplified. We can move this here. This can be removed. Yeah, this should not be here. No, but this comma is a special case for the comma. Oof. The last one doesn't have a comma. Yeah, this is better. So we do call get token. If it's r parentheses, we directly go to r parentheses. We directly go to body function. Otherwise, we read it as a type. And this one will also read the, yeah, this one will check if it's a comma or a curly brace. Sorry, if it's a closing parenthesis. If it's a closing parenthesis, it will go to the body. If not, it will again consume one type and then go back to parse. Fine, this is okay. Okay, now let's also register the function in the function table, in the symbol table. So the weird thing about functions is we should just store the return types. You don't have to store anything else, which probably means we don't need to do this push either. Yeah, we can just get done with this. Okay. The code for adding to the global symbol table here. Okay, so global symbol table and RAX, move R12 into RAX R14, which is the start of the current code gen area, into RAX. Perfect. R11 into AX of 16, which is the address type of return type of this function, which is fine. We need it. And then we have 24 RAX. That's correct. So global table has been updated, and we haven't shifted the address yet because the body of the function will be generated as we go. Okay, great. Now we just need to handle parse statement. Right, so we jump to function and it returns back directly to the, okay, this is great. We haven't pushed anything now, right? No. Okay, great. So body is being parsed, parse statement. Okay, that's what we're going to do now. Parse statement. So for now, parse statement is simply going to keep eating up tokens till it sees a semicolon. We just want to make sure that everything runs correctly. So in parse statement, the first token has already been consume, so it's already in RAX. So we have pasted a while loop essentially. What's the parse statement? Compare q $token underscore semicolon comma %rex. Jump on equal statement done. Otherwise go back. Otherwise read the next token and jump to parse statement. Yeah, so this will basically just consume all the statements inside, all the tokens inside the statement, and go back to call. And eventually when it's done, parse statement done will simply return Q. So this will go back to parse statement. This looks correct. Which one is this? Why doesn't it complain? Forgot to do some. Wait. Yeah, this is fine. Current function slots, current function slots. This also looks fine. God, I have on parser.o. Relocations against data cannot be used when making a py object. I must have referenced it wrong somewhere instead of. What data sections does this have? We have current function slots. That must be it. Oh wait, I think this is the problem. This can't be 0, it has to be $0. Nope. It's going to put its own address for now, but I think 0 should be fine. Yeah, this is not an issue. Let's refresh to current function slots where all it is referenced. Okay, so the first time it's referenced is move 0 into current function slots of RIP. This is fine. The second time we move from it into RBX. Third time this is fine. This isn't an issue then. Global symbol table, local symbol table, local symbol table, and local is what we added, right? Local symbol table. Yeah, local symbol table. Oh, what? Right? Yeah, this was a mistake. Ah, that works. Okay. Hey, it went to completion, which means must have run correctly, right? We will check. So we reached parse function. we entered it into the global function table. Great. Okay, so we check if it's a closing parentheses or not, which it, sorry, no, not closing parentheses. We check for, yeah, closing, yeah, right, okay. And then parse function body, perfect. We get the first token, which is the curly brace, that's gone. We get the next token, which is the first token of the next statement. In this case, it should be return, right? Oh, got stuck. Ended quite early. We didn't parse the return or anything. Yeah, there's a curly brace and then return. It's parse function body we do get next, and this should be the curly brace, which is 7b. That is opening 7. Oh. CHR of 0x7b is opening curly brace. Perfect. So we pass the opening curly brace. Then we parse the next token, which should be return, but this one gets stuck, so we do step I. Why did I identify it? It should be return. Okay. RETURN. It's like 726574. 726574. Return. 72657. Perfect. This is correct. Oh, so it did work fine. Why did it get stuck last time? Okay, next I. So this must have consumed the semicolon, and we get the next token. So next I stashes $RAX. This should be 7D, which is the closing curly brace. Perfect. Next I parse function body next. This goes, okay, it is equal to curly brace, and then we read from this. Okay, this is perfect. Yeah, goes to parsing n. Okay, so we have variables being passed and created, functions being created. Now we just need to do statements. So statements are tricky. We should handle one by one statement. We haven't created any code for the function yet, including things like stack frame allocation and any of the like preamble of the function, whatever it is, like push RBP and stuff like that. So we'll do that later, but we'll start doing the bulk of the function, which is the body of the function. And this is where we actually start generating assembly now. But instead of generating assembly, we would be generating object code. So we're going to put instructions out directly. Yeah, so let's do parse statement. Okay, so we check the first token. If it's semicolon, then it's done. If not, we have to handle. It. So now we check if it's the return statement. So we say we'll start handling statements by statements. There's only I'm going to put some comments here. Statements can be of the form return expr. Just expr. If expr statement else. It has to still be syntactically valid C++ code. Or it can be while expr, and that's it. These are the only type of expressions we're going to handle. Oh, and also variable declarations. So wait, do we want to handle local variable declarations? We probably should. Type identifier. Yeah, so it's going to be either a return of an expression or just an expression, or it's going to be a type and then identifier or while. Okay, so the reason yeah, this just makes it easy to pass all statements. Okay, so let's handle them one by one. I think they're going to be, if while and local declarations will handle later, we'll just do return an expression, just like standalone expressions first. So compare token keyword return. With %ix. So if it is a keyword return, then we say, should we just do it right away now? Should jump an equal parse return statement. And for now, I'm just going to say invalid statement. All right, let's go. Okay, now let's do parse return statement. So what parse return statement does is it needs to first call the code for the expression that comes after, right? So we have already consumed the return keyword, that's already done. Whatever comes after, we just say call parse expr. So whatever expression comes after it, we just parse that. And then we will have to return from this. No, we parse the expression and then we do get token to consume the semicolon. So when parsing expression, sometimes we actually might have to consume the next token, um, because we don't know when expression ends. So we need a mechanism to like we need to say like parse expression is going to consume an extra token. So we will have to stop here. We'll say um, semicolon already consumed by parse expression. Because parse expression needs to know when to stop, and the only way it can know how to stop is if it has already consumed a token. And the reason for that is, think about if you have expressions like a plus b, it could also just be a. So you parsed a, you got an identifier, great. Then you parsed whether to stop or not. You'll only know if it like if you see a plus next. So we have to parse the next token. Yeah, so expr will always consume an extra token, and then we just return from this parse statement. We need to do code generation here, so to do code generate for return, which will just mostly look like popping a value from the stack in the actual execution stack and then returning that value. Yeah, so now let's write the hard part, which is parse expression. This parse statement done is not required anymore, right? Yeah, the statement cannot just end in a semicolon. Maybe it can. We could have empty statements. Yeah, so let's do that. Yeah, we do want to allow empty statements because sometimes you just have to write empty statements. It's annoying. We also need to be able to handle empty blocks of function, which means, yeah, we can add a code here. So when it says parse function body next, this actually goes yeah, this one is assuming that there's always one statement inside the body. Parse function body, consume the curly brace, then consume the next statement. Actually, we should just check it right away. Say if it's equal, we say parse function body end. Otherwise, you parse statement, call get token, just jump to parse function body next, which means we could get rid of this and move this here. Parse function body end. Okay. Yeah, this will make sure that if there's a curly brace, immediately it'll be skipped. Okay. Now we're doing parse expression. The parse expression is quite complicated because, again, we have to first write the types of expressions that we can have. Expers can be of the form integer An integer itself is an expression. It can be an identifier, right? And then can optionally have a binary operator, an expression, right? Or we can also have parameter, L-param expression. So we don't want to handle the precedence of our operators in the compiler. So we're going to require that the user has to add parentheses around nested expressions, which should go nested expressions must be under parentheses. Also, I haven't been adding this properly. I do want to remove the limitation of having white spaces ending the tokens. It takes a lot of work, but I think I'll eventually get it done. So this should be here. I don't know what I was doing on writing this website. Let's check if this looks correct. Okay, this is somewhat better. Okay. Let's go. So expressions can be of the form this, or this. Optionally have a separate binary operator of expression after it. There could also be a unary expression. Optionally have at the beginning no, we should just say unary operator of expression. Yeah. Right, so it can either be unary operator of expression, or it can be a curly brace expression, or it can have an integer, it can be an identifier, or it can also have a binary operator expression. We'll add function calls later. Okay, so let's handle integer expressions first. So parse expression, by the time we enter, have we already consumed the first token? We haven't. We just consumed the return statement. So we'll start consuming the very first token. So we do call get token. Okay, then we compare it against keyword, no, not keyword, token integer, right? Token integer, yeah. Let's handle the simplest case of token integer. So this is the benefit, by the way, of being able to like compare entire literals together into a single command. Like if it was an integer, I have to like one by one check each character if the whole thing is an integer and stuff like that. So it's just easier if you tokenize it. You can just compare the whole token in a single go. So I'm going to check if the next token is an integer. If it is an integer, I jump to parse integer constant, right? Parse integer expression. And as usual, we will leave an invalid statement or invalid expression. Error message behind. Right, so now we have parse expression. Now we just need to write parse integer expression. So this one, the token is already consumed. We just need to generate the code for pushing this token, this integer, onto the stack. So this is where we actually start generating code, which means we need to start writing bytes. So let's separately first for ourselves see the kind of code that we want to generate. So I'm going to make a scratch directory. I'm going to write a simple function that just does move q. So in the generated code, we'll always use RAX and RBX as like scratch registers as usual. So suppose I want to do 0 to RAX, and then I want to do push q $RAX, right? This is the code I want to generate. So it'll be bj dump dash st.o. Okay, so we get this instruction. So we get 48 c7 c0 blah blah blah. So we just need to load this into a register and then generate this code. So it's the easiest way to do this. We just write the literals out, and it is little. Just want these orders, so it has to be the bytes have to be flipped around, but yeah, because Indian. So we do move q. The value of the integer constant is in RBX, so we can't touch that, but we can write the add bytes, right? So what was it? We need to write 48 c7 c0, which is 3 bytes followed by 4 constant zeros. Okay, so we first actually we should check what happens if I want to add a different constant. Yeah, so suppose I want to say a b c d as a constant I want to write. Bad. Dollar a b c d 0x, right? It's a constant. I was thinking of it as a label. Okay, so we get CDAB. So if I want to write the byte order just needs to be matched correctly, but either way 48c7c0 needs to be written, so I'm going to write that. Move b 0x 48, and we are writing this at R14. This is our code generation area. B48 C7 C0. And now we can just dump the whole integer. So we can say move, what is it, L, %ebx, comma 3 of %r14, and then finally we do 50. Move p 50, comma 1 2. So this is 4 more, so 7 of R14, and then we simply increment R14 by 8 because we are putting down 4 bytes of data. There we go. That is our return. That is our return instruction with whatever. Sorry, not return. This is just pushing an integer constant onto the expression. Yeah. looks right to me. We'll have to debug this. Yeah. Okay, so we have the integer expression done now, so we do return from here. This will return directly out of parse expression itself. No, so yeah, so since this was, we haven't finished parsing rest of the integer yet, rest of the expression yet. So we go back to like parse. So for now, we are directly going to consume the next token and return. We'll assume that it is correct. So when parse statement calls parse expression, it calls parse return statement, semicolon is already consumed. Okay, this is correct. Okay, so oops, we have parse expression, which calls parse integer expression, which just go back to parse expression continue, right? We haven't done parse return statement yet. So this one now need to generate the code for it. So go back here, we do pop q %rax and then return q. We generate this code now. So we do so it's always going to be 58c3. So we simply do move b $0x58 into %r14, do move b $c3. Great, so this does parse return statement 2. I think this should be good. This will be able to handle our very first program that we have been trying. So let's first fix these errors. So just error in symbol invalid statement is already defined. Number of operands search for compare. I forgot the comma. Why is this not working? Keyword return comma rax, literally the same thing as above. What? Operand type mismatch for comparison. Is it that not keyword underscore return? It is keyword underscore return. Oh, but it's too long. Yeah, so the constant is too long, so we can't directly compare it like that. 64-bit constants can't be fit into a compare instruction, so we need to move it into some other register first. So we do move absq $keyword return into %rbx, right? rbx should be fine because we just compared. No, we can't use rbx either because it could contain the keyword or identifier, so we use rcx. Okay, that works. And it spins, so this must be correct, hopefully. Parse function body. Yeah, this is fine. Okay, so we are at the function body now. Next I. Got stuck. Make sure that it's actually getting stuck. Yeah, next I get stuck. Why? Goes into parsing in. Let's check what the token is. Where did this come from? What's the last token? 29. What's 29 again? Okay, yeah, this is fine. Just closing parentheses. So why is get token getting stuck? Let's step I. It's opening braces, okay. Next I. This is a special character, right? Wait, it's not a special character? Oh, this is in the middle case here. Yeah, special character. Wait till the end. Consume spaces. Wait, why was it getting stuck earlier? I'm so confused. Okay, p/x $array x is 7b. That is opening curly brace. That's good. This is the keyword return. Great. parse statement go inside. Parse statement 3b with RAX. This is the return. So it goes to parse return statement. Perfect. Call parse expression. So it's step inside. Next it's parse integer expression. Tuck, 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 tuck. Parse expression continue. Calls get token and get stuck. I do next on next I did next I should just do step I. I'm guessing this is the okay. At this point we can just check if the function is correctly generated. So we just do x of codegen buffer. It's all 0, 0, 0s. Oh, that must be the integers, right? So x comma 32 codegen buffer. Okay, so we have some instructions. Let's go. We finally have some instructions. We have 1, 2, 3. Okay, how many bytes are these? 1, 2, 3, 4. 1, 2, 3, 4. So this is 4 bytes. First two integers, second two integer, third. There's 3 variables at the beginning, and then we have a 0, 0 at the beginning. C0, C7, 4, 8, 5. Why is there an extra? C0, C7, 4, 8. Oh, it's backwards. C0, C7, 4, 8. Wait, that's interesting. I wrote 4, 8, C7, C0, and it got C0, C7, 4, 8. That's so. Oh no, these are. This is. I need to dump it as. Grouped as a single byte. In Gemini, how do I, in GDP, how do I dump part of an array as individual bytes encoded in hex? Yeah, x. Oh, count format size. So x counts format xb. So it will be x comma 32 xb. Codegen buffer. Let's go. Okay, so we have the first 3 variables, and we have 48 C7 C0, and then 4 zeros. That's correct. And then we have 50, which is the push. Let's do 64, and then we have after that 58C3, which is exactly what we expected. Perfect. So we have our push and pop instruction. We can actually also do DISAS codegen buffer, which will show us the disassembly at that point, and we have our correct code there. We have 0x0 RAX Right. Perfect. This is what we wanted. Now let's also try changing the constant a little bit and make sure that the constant arrives correctly. So let's say we put 1, 2, 3 here. Um, just run this, Control B, and then we can simply do diss codegen buffer. We do have 7b. Is 7b correct? Is 7b correct for 1, 2, 3? It is 1, 2, 3. I want a 2-byte number too, so I want to do 0xabcd 43981. 43981. Okay, that is wrong. We got 82D5. 43981. It's supposed to be ABCD. Yeah, so our integers are not being parsed correctly. That's okay. We will fix this. 80D5 for some reason. What is 80D5? 32981. Interesting. What about D580? 54656. Yeah, this is completely wrong. Okay, let's make sure that the integers are passed correctly. So we put a break on tokenize integer, right? No. What is it called? Get token integer. Okay. At this point, we should check what RBX is. It's 32981. Did I write it wrong? Oh God. Idiot. Okay, DSS codegen buffer. We get 0xabcd. Let's just make sure that if I write that if I add 0xabcd, I should get 0xabcd, right? It does appear correctly. Okay, so we have 0xabcd appearing as 0xabcd. Perfect. Right. So now we have our return expressions done, but expression is not completely done yet. We should, but before we go ahead, we should try running this code. So what we're gonna do now is when all parsing is done, when tokenizer goes and says, hey, I'm done parsing, parse, what is it? End. Yeah, program parsing end. We are actually going to just execute the program. So at this point, like, everything must be ready. All that needs to be done is just look up the address of main and look up the address of main and and jump to that address. That's basically what it is. So, and to make it easy for us to find the address of main, what I'm going to do is in the identifier table, I'm going to fill some data of our own. But this is going to make this extremely hard. This is BSS section now. Oh God. I want a pre-populated identifier table. I guess I could just put in this in the data section. Okay, I'm gonna ask Gemini. Contest section in GSM. I want a table with the first few bytes as I said them, and the rest should be uninitialized. How can I do that? You can achieve this by combining the byte long with space or skip. So I can do, yeah, okay. Instead of doing it this way, I'm gonna do identifier table, and then I'm gonna put the very first identifier as main, so that way we can always just refer to main by identifier index 0. And because when it parses, the tokenizer parses, it first checks if the identifier exists, so it won't create a separate main entry, it will just always exist. And all I need to do is like get what the main's token is, which should be easy. It's like m gets first parsed and shifted. It's just the bytes of main. It's just not that hard. Dot quad. We already have a program that does it, right? Just run this. Here it is, 606169CE. So this is the string representation of main. But remember that it's actually 4 entries per identifier, not just 1. So we need to have 4 zeros after that, 3 zeros after that, sorry, because each identifier can be up to 16 bytes long. And then we do space 40960, where we have no space for the rest of the identifiers. Okay, good. So we now have the main identifier filled in. Now what we are simply gonna do in our tokenizer is this program parsing end. Unfortunately, maybe we can just return out of this, but the problem is the caller now has to check, hey, if this is the last token, and every single thing has to check if it's the last token, which makes things a little tricky. Although the last token will always be either a curly brace or a semicolon. Like wherever it's being checked, it'll either be, if it's in the middle of, like if it's the end of the function, it has to be a curly brace. So wherever you're checking the body of the function, you can also check if it's the end of the translation unit, and then return from parse parse tu, and then let the driver call the code. That's the cleaner way to do it. I'm feeling, yeah, we should just make a token for the end of parsing. So let's go back to the defs again, and I'm gonna say token EQU token of EOF 0x. So we just need to give it some identifier. You can just do it 0x0. Token 0 is just EOF. right? Okay. And now what we do is parse in just returns that token. So move q $token EOF into %RAX with q. What is program parsing and being called from? I just want to make sure it's called. Yeah, this is fine. Literally just from the beginning of the get token. Huh, that's interesting. It should also be called from consume spaces, no? Or it will be checked on the next time when token end is called. Yeah, that makes sense. Yeah. Okay. So this simply returns token EOF, and token EOF needs to simply be checked at the beginning of parse TL. So here it is, parser parse TLD, right? So it says parse TU. When you enter parse TU, the first token has already been parsed, right? Where did it call parse TU? Oh, it immediately calls parse type because that's the very first thing, and then parse type does call get token. So what we are simply going to do now is we are going to call get token here, and then we can just go to parse token no read. So, and then before that we check if it's a EOF token. Before passing the translation top level declaration, we check if it's EOF. So we do comparison token EOF comma %RAX, and if it is equal, we go to parse TU end, otherwise we call parse every node, and then we do here parse TU end, which is just return Q. So this is done with parsing all the top level declarations, and then we go back to driver, and this one just returns now, which is fine. We can test it out. Parser expected type. Okay, let's change something that made everything wrong. Run parse TLD parse TU. Let's just step through this. Parse type no read. Oh, wait. Parse type might. It is x86c74, which is int. Parse TLD. This is identifier. It's a global variable, so we go okay. So second one, actually just break parse tu. Continue. Okay, so we got parse tu. There's too many things happening. How many times did parse tu get called? This is weird. Okay. Parse tu is called. We had break on parse tu. Sorry, we had to put a break on parse TLD. Three, 4, 5, 6, 7, 8, 9, 10. Wait, this is bizarre. I mean, there are some wraparound issues here. Let's just step through one of these. So we do next token. What did we get? We got 0. It's correct. So we do next I. It goes to parse tu n, which should go to return. Oh, wait a second. For some reason we had parse tu being called parse TLD. Oh, it needs to go parse TLD end, not parse tu end. It needs to be parse TLD end. Right. But tu somehow needs to know that it's done and return from it. Use error codes, or we can just move this here. Yeah, okay, this is fine. Okay. So we first check the first token. If it is end of file, then we just immediately jump to TLD end, not TLD end, tu end. Otherwise we call parse TLD and then go back to parse tu. Okay, this should work. And it does work, it exits normally. Perfect. Now let's try to actually call the function and see if it executes. So now the driver needs to execute program. So at this point it just needs to do call execute program, and execute program will also return back to this point. Honestly, we can just jump to execute program, and this can be unreachable. Like, yeah, we don't. I was thinking we'd call and then return the call value, so in case we want to do something on the compiler side again, but I think this is okay. We can just jump into it. Okay, now let's put that into execution area. So this goes into text section, execute program, right? Execute program, yeah. All right, so we need to somehow find the address of main and then jump to it. So we know the identifier number. So we first do move q, the index of the identifier we know is 1. It's always 1. No, 0, sorry. Identifier index of main is 0. Var it. Okay, we need to now go to the global symbol table and find the address. So LEAQ global symbol table IP into RBX. -8% RX, RX. Check next function. A symbol table needs to have, we need to stop once we reach end of it, so we do comparison. Global symbol table end of RIP with RX. If we have reached the end, then we jump to main, jump on equal main, no, yeah, jump main not found, which takes an error message. Main not found MSG. Okay, this is why I don't like moving it around. Main not found MSG len. And then we have move LAQ main not found message $% IP comma RBI move Q main not found message len of %IP. No, it's a constant. To RSI and then jump to report. Okay. If we have reached the end, we have gone too far, something is wrong, and then we do comparison of the value at RAX with so we don't need to put this, we can just compare it with 0. Compare Q RAX of 0. If jump are not equal, go back to check next function. Okay. Yeah, this is good. And then at this point we have found main, we get its address. So move q $rax. Second was type add global table. Global symbol table has identifier code generators type of variable. So we have identifier code, right? So we do move q 8rax comma rax. This is the address, and then we simply just jump to rax. And that's it. That should execute the function. Jump compare 1682. Alright, one more issue. Main not found message line cannot be used when making a P object. MS. And if I reference to execute program, it's to be global. Undefined reference to global symbol table. Global symbol. Oh. Also, this contains the value. This needs to be here. There we go. It works. Alright. Check next function is failing. That's easy to debug. Let's actually put a execute function. No. Execute program. Reached here. What is this doing? Yeah, I made some. What is it? Yeah, and compare. Why is this a compare? This should be move. Did I not compile this? Execute program. this is n. Okay, it exited with 0315. Is that correct? That seems wrong. I did it with 0315. I think it was supposed to return with whatever that function returns, right? It's not 0315. Okay, let's just wait, it found this easily. Yeah, it's about to. This is wrong. Global symbol table. We didn't put stuff in the global symbol. We put in the identifier table. And the first of the global symbol table is identifier index. Yeah, something is wrong. It's not main. The global symbol table somehow has main in the first one. That doesn't make sense. Debug the global symbol table. Okay. Let's print it out first. So piece slash x slash 32 global symbol table. So we have complete this array. The first entry says 0. That is weird. What is identifier table saying? x32 xpf identifier table. The 0th entry is 6f6f66. Right, because we overwrote from the beginning. So we go to tokenizer. Identifier table n should not be here. It should be identifier table non or start. And this should be identifier table start. Okay. Let's just try running it. File not found, of course. Huh? Did I change the name for? Yeah. Main And this might be an off by one error. Compare RBX. Okay, this is so C0 and 20. Okay, not a problem. I'm advancing by 8. That is wrong. It should also be advanced by 24. This needs to be 24 because each global table is 24 bytes, not. Yeah. Main function not found. It's reaching the global symbol table end. Okay, so we got okay, so it's C0, C0 and C120. Okay. It's 1. Okay, the global symbol says 1. So this is not correct. It's already gone to main, not found. Two, three, not the same. What the hell is it? 0xFFFF. Where did this come from? Why is it FFFF? I think it's when the main function gets passed, it's somehow getting its index as -1 because it subtracts from. Why is it getting -1? Somewhere wrong here. So identifier table start. Okay. Let's look for parse identifier. Get token token identifier. What is it called? Identifier and keyword. Just a store identifier. At this point, we are ready to store. The identifier must be in RBX, RCX, RDX, RSI. So let's do 6666FF. This is what? Foo, maybe. Yeah, foo. Six two 6172. This is bar. Correct. 62617A is Baz, and then there should be main after this. 6061696C. This is main, right? 6061696C. 60616. Okay, perfect. So we have main now. So we have the global symbol table, sorry, the identifier table loaded. Let me go it back a little bit. Okay, /x$REX. We have 8090. What is the address of identifier table? It's also 8090. Perfect. Next I. Checking if we have reached the end. We haven't, so we go ahead. RBX, RAX. RBX is 66169C. This is correct. And then RAX is also 66169C. So this is correct. Next I. This should also match, this should also match, and this should also match. Now we go to store, identifier, finalize. Okay, here. We take global symbol table is identifier table. No, identifier, no, that's fine. Just the identifier table again. Mistake. Can I go back? Okay, this is correct. Now let's go further. Store, identifier, finalize. Okay. I got 0, 0. Why do we have this D, C then? To add this DC for something. Yeah, this is the one that was compared. This is correct. I guess the... Oh, right. I know what is happening. So this, when it finds it, we shouldn't provide, we shouldn't subtract 1. Right. Yes, this one. This is only required if it doesn't match. We could just do this here. Just simplify it. LEAQ 32 of RAX, also this should be 32, not 8. Yeah, when checking you should check not one by one, you should check the whole thing. Okay, this should be correct. Wait. Yeah, that's correct. Seems like valid address. Why did this set fault? What? Is it not called execute program? Let's call execute program. Oh, it's never getting to execute program, is it? Check next identifier. I thought it was check next function. Okay, somehow this one is failing. This is also wrong. Finally, but it's also ending in 0315 for some reason. Okay. Now we can actually step into this. So I'll check a few functions. It's gonna find finally the address of which is gonna be somewhere in the middle of code gen area, not the beginning, right? Let's look at it. Code gen buffer is A0C0 A0D8. Perfect. This is great. I do next I. It does go here. ABCD into RAX. So we go next I. Next I. correct. This goes to libc start, which is also correct. Program ends with 0315. That's weird. Let's try to run it without GDB. It's 205. Why is it 205? It should return a value that 43981 not correct. Let's say 42. This is correct. This is also correct. Then why was it 43? 43981. I'm not supposed to return values bigger than. Is it truncated or something? 205. What is 205? What is CD? Wait, does libc truncate the last byte? Maybe. I don't know this. Does libc underscores start when a program is run in bash and the main function of that program returns an integer, how does that relate to the variable $? Oh, this is the most important gotcha for assembly and system failure. Might use a 64-bit RDI to hold your Linux one uses the least significant 8-bit for the exit status. Well, I did not know this. Great, but we do have finally a bunch of a value being returned from our program. Which is great. Should change it to something smaller. Let's just keep it 42. And we get 42 out of it. We finally have a simple program compiled 7 hours into the stream. I do want to add a little bit computation to this, so I do want to add maybe variables being set. Yeah. Maybe like the global variables being referenced, those would be nice. We don't allow setting variables yet though, so we have to do assignments. Okay, let's go to parser. Parse_expr. Expressions can be of the form. It's actually missing one more thing, which is what happened to my syntax highlighting? Why is it broken? Expressions can also be of the form binary operator export. Yeah, so this will include assignment if needed. Yeah, okay. I'll quickly put some changes and then we will get to writing some more. yeah. Basic empty return value function working. Alright, we have some basic expressions working. I quickly want to handle addition. Um, then we can do more complicated stuff next. So let's do one binary operator. Actually, if you do one binary operator, we can actually do most binary operator, because instead of writing special cases for each operator, we'll just maintain like a table of operations and their corresponding byte of like instructions. That's a trick that I found in the sector C compiler when I was reading through it. It's a cute trick because it's very easy to then add more what should I call it, operators very easily. Also, at this point we should check how big our executable is. It is 62 kilobytes, which is still a lot. I don't understand where this is. This is gonna be hard. Let's see. Are we unnecessarily filling up pages? Actually, I want to know each section and its sizes. So BSS is, data is also large. Sizes here, sorry, I was looking at the wrong way. Yeah, data is large. BSS is also large. This is taking up so much space. Wait, is this size as in like size in bytes or? No, file offset is what we should be looking at. Okay, yeah, this section is large. Data section is for some reason going from D to 3 to D. It's taking majority of the space. Yeah, these are small. So like init is small. Text is what? 1204 to 15 F0, which is like very small. RO data is reasonable. These are fine. Dynamic is fine. I don't know why data is taking so much. BSS is obviously empty because there's no BSS. Let's look at all our data sections. Let's start with tokenizer. I think I might have left it as, yeah, this identifier table is in the data section. Can I make this into BSS? Let's see, just ask Gemini. I have a section defined as so. The 10K 40K worth of space is being added to the binary. How do I don't care for it to be initialized to a particular value. How can I make sure it doesn't occupy any space in my binary? No, but this is but I have other dot data and dot bss sections in the program. I want yeah, but that's not true. The most of us need to define your labels together in one place, even if you switch sections in between. What? The assembler will treat them as single logic unit for the specific file. Yeah, I think this might be the best way to do it. Just use programmable bits. So now we have a table data with programmable bits in the beginning, and then we have non-bits. And this should be fine. So this becomes ident table. Okay, we're down to 21 kilobytes, which is good. Just to make sure there's no other. Oops. No large dot data sections is what we should do. Dot data is fine. This is okay. This is okay. Just 2 bytes. This is a keyword table. This has programmable bits we need it. Okay, this is fine. src parser dot data. This is fine. These are okay. Execution area. This is anyway separate and it has no bit, so this is fine. Driver. Yeah, this was the program area, right? Token read head. But this was BSS anyways, this is fine. So program source. Why is it still occupies 21 kilobytes? Okay. Down dash h. Let's see. Data section is shrunk to 98 bytes now, so that's good. Ident table is some number of bytes, that's okay. Yes, the majority of it is being occupied by what is occupying so much space? 21 kilobytes is a lot. How much is 302p? It's 12 kilobytes. So where is the rest of the 8 kilobytes? The comment section? Oh, it's small. There is a way to check this. I'll do it later. Oh, it is read ELF, right? It'll tell us everything. Dash H. This is the header of the whole program. We want section headers. Capital S. Entry size is what we care about. Of type, address, offset, size, and size, flag, link, info. just 2028. This is EH frame, so it's not ours. It's fine. We can strip this. We can try stripping it. Yeah, strip. Check how much is this now. Still 14 kilobytes. Okay, we'll debug this later. It's 5 p.m. now, which is 7 hours into the stream. I could go for another hour. I should maybe take a break. Yeah, I think we should end the stream at this point because we have something that's reasonable. I'm just gonna commit these changes. Moved identifier table to separate section. Yeah, so we'll stop the stream here today. It's been 7 hours. I really wanted to finish to a point where we can like run factorial or something and maybe print some integers, give like a basic runtime library to the program, but unfortunately that's not going to happen right now. But we'll do this. We'll continue the stream off from here maybe next week, and we'll finish this project. All right, thanks everyone for joining. Let's continue this next week.